Picture our world as it exists right now. Beneath your feet, the ground moves at over 1,000 miles per hour if you're standing at the equator. Yet you feel perfectly still, cradled in the gentle embrace of physics that has governed our planet for billions of years. This spinning motion, this endless dance through space, shapes every moment of every day, every breath you take, every wave that crashes upon distant shores. But what if, in an instant, it all came to a halt? The ancient dance of our world, to understand the magnitude of such an event, we must first appreciate the miracle of Earth's rotation. Our planet spins because of momentum inherited from the very dust and gas that formed it 4.5 billion years ago. In the early days of our solar system, vast clouds of cosmic material swirled and condensed, each particle carrying angular momentum that would eventually become the rotation we know today. Imagine yourself floating in space, watching as countless specks of matter spiral inward, each following the laws of physics that demand the conservation of angular momentum. As this material draws closer together, the spinning motion increases, much like a figure skater pulling in their arms during a spin. This is how our Earth began its eternal waltz through the cosmos. The Moon, our constant companion, plays its own crucial role in this dance. Over the eons, its gravitational pull has gradually slowed our planet's rotation through tidal forces. In Earth's earliest days, a day lasted only about 6 hours. The Moon's influence has stretched our days to the 24 hours we know, creating a rhythm that governs all life on our planet. This spinning motion affects everything around us in ways both subtle and profound. The Coriolis effect, born from our planet's rotation, guides the movement of winds and ocean currents. It determines which way water spirals down a drain in different hemispheres, though this effect is so gentle that it only becomes noticeable in large-scale systems like hurricanes and typhoons. Our atmosphere, too, is shaped by this rotation. The jet streams that carry weather patterns across continents exist because of the temperature differences between the equator and poles, combined with the spinning motion of our world. Without this rotation, weather as we know it would not exist. The very air we breathe is distributed around our planet by forces born from this ancient spinning motion. Even the shape of our world reflects this rotation. Earth is not a perfect sphere, but an oblate spheroid, slightly flattened at the poles and bulging at the equator. This bulge exists because the centrifugal force of rotation pushes material outward most strongly at the equator, where the rotational speed is greatest. The difference is subtle but measurable, with the equatorial diameter about 27 miles greater than the polar diameter. Deep within our planet, the rotation drives the movement of molten iron in the outer core, generating the magnetic field that protects us from harmful cosmic radiation. This magnetic field, our invisible shield, exists only because our planet spins and contains the right materials in constant motion within its depths. The moment of stillness now, let us imagine the impossible. In a single instant, without warning or gradual change, Earth's rotation comes to a complete stop. The planet itself becomes motionless in space, but everything upon its surface continues moving at the tremendous speed it had moments before. This is where the fundamental law of inertia reveals its awesome power. Objects in motion tend to stay in motion unless acted upon by an external force. Every ocean, every cloud, every building, every person on Earth would continue moving eastward at the speed they possessed just moments before the planet stopped. At the equator, this speed exceeds 1,000 miles per hour. In New York City, it would be about 750 miles per hour. Even in northern Canada or Siberia, the speed would be several hundred miles per hour. Imagine the magnitude of this momentum, accumulated over billions of years, suddenly having nowhere to go. The atmosphere would continue its eastward motion like a great river of air flowing around a suddenly stationary Earth. Winds beyond any hurricane ever recorded would sweep across the surface, carrying with them everything not firmly rooted to bedrock. These winds would reach speeds that dwarf the most powerful storms in recorded history, creating a global atmospheric catastrophe that would reshape the very face of our world. But the atmosphere is only the beginning. The oceans, containing billions upon billions of tons of water, would also continue their eastward journey. Picture the Atlantic Ocean as a massive wave, taller than any mountain, racing across continents at incredible speed. The Pacific, with its vast expanse, would become a moving wall of water that would dwarf the tallest skyscrapers, sweeping across Asia and the Americas with unstoppable force. These waters would not simply flow like a river. The sudden stop would create a complex pattern of waves and currents as different parts of the ocean, moving at different speeds due to their latitude, would collide and interfere with each other. The resulting chaos would reshape coastlines and create new ones, carving valleys where plains once existed and depositing ocean floors on what were once mountaintops. The solid crust of our planet would experience forces beyond imagination. The continental plates, suddenly subjected to unprecedented stress, would crack and shift. Earthquakes of magnitudes never before recorded would ripple around the globe. Mountain ranges would crumble under the force of the moving atmosphere and oceans, while new ones would be thrust up by the buckling crust. In populated areas, the consequences would be immediate and absolute. Every structure built by human hands, every city, every road, every bridge would face winds and forces far beyond any engineering specification. Buildings would be swept away like leaves before a hurricane, their materials joining the great eastward flow of debris circling the new motionless world. The great atmospheric rivers, as our stationary Earth faces this atmospheric onslaught, the patterns of air movement would create phenomena unlike anything in our planet's history. The atmosphere, no longer held in its familiar rotation by the spinning surface below, would develop its own complex dynamics. Picture vast rivers of air flowing from west to east around our motionless world. These atmospheric currents would be unlike the gentle trade winds or even the fiercest storms we know today. They would be persistent, powerful streams of moving air that would fundamentally alter the distribution of heat and moisture across our planet. The temperature differences between day and night sides would create enormous pressure gradients, driving winds of incredible velocity from the hot side toward the cold side. But the Coriolis effect, which once guided these air movements in curved paths, would gradually diminish as the atmosphere adjusted to the new reality of a non-rotating world. In the initial hours and days following the stop, the atmosphere would be in complete chaos. Turbulence beyond any scale we've ever witnessed would dominate as different air masses, no longer constrained by the organized patterns of rotation, would collide and mix in unpredictable ways. Imagine tornadoes the size of continents, their bases stretching across entire countries, their tops reaching into the stratosphere. The jet streams, those high-altitude rivers of fast-moving air that currently guide weather patterns around the globe, would disappear entirely. Without the temperature gradient between equator and poles being organized by rotation, these streams would dissipate into chaotic, turbulent flow. Weather prediction would become impossible, not just because of the complexity, but because the very concept of weather systems as we understand them would cease to exist. As the atmosphere gradually adjusts to its new reality, different patterns would emerge. The fundamental driver would become the temperature difference between the day side and night side of our planet. Air heated by the eternal sun on one side would rise and flow toward the cold side, where it would cool and sink, creating a simple but powerful circulation pattern. This circulation would be unlike anything in Earth's current weather systems. Instead of the complex swirling patterns we see in satellite images today, we would have massive linear flows. Rising air on the day side would create an enormous low-pressure system, while the night side would become a high-pressure zone of descending, cooling air. The boundary between day and night, the terminator line that would now be fixed in place, would become a zone of perpetual storms. Here, the hot air from the day side would meet the cold air from the night side, creating a ring of thunderstorms and severe weather that would circle the entire planet along this boundary. These storms would be fed by the constant temperature difference and would persist as long as the sun continued to shine on one side of our motionless world. Clouds would form in entirely new patterns. On the day side, the intense heating would create massive convective currents, forming towering thunderheads that could reach altitudes far higher than any clouds in our current atmosphere. These storm systems would be fed by moisture evaporated from whatever water sources remained, creating a cycle of evaporation and precipitation unlike anything in our planet's history. On the night side, a different phenomenon would occur. The rapidly cooling air would struggle to hold moisture, leading to widespread precipitation as water vapor condensed out of the atmosphere. But this would not be gentle rain. The massive air movements and temperature differences would create precipitation events of incredible intensity, with hailstorms and freezing rain occurring across vast areas of the dark hemisphere. The oceanic transformation, while the atmosphere rages above, the oceans would undergo their own dramatic transformation. The initial catastrophic movement of water would eventually give way to new patterns of ocean circulation, driven by temperature differences rather than the Coriolis effect. Imagine the Atlantic Ocean, no longer constrained by the familiar patterns of the Gulf Stream and other rotational currents. Instead of the complex swirling gyres that currently distribute heat around the globe, we would see massive, linear flows of water moving from the hot day side toward the cold night side. The day side oceans would become incredibly hot. Without the cooling effect of evaporation being distributed by wind patterns, and without the moderating influence of ocean currents, surface temperatures could rise to levels that would make the water almost too hot to sustain most forms of marine life. The intense heating would drive enormous amounts of evaporation, feeding the massive storm systems in the atmosphere above. This heating would create powerful convection currents in the ocean itself. Hot water would rise from the depths while cooler water would sink, but the patterns would be much simpler and more linear than our current ocean circulation. The three-dimensional complexity of modern ocean currents, with their interactions between surface winds, temperature differences, and the Coriolis effect, would be replaced by straightforward thermal circulation. On the night side, the oceans would face a different fate. The lack of solar heating would cause surface temperatures to drop rapidly, especially in areas far from the day and night boundary. Ice would begin to form, starting from the poles and the areas furthest from the sun, and gradually expanding toward the terminator line. But this ice formation would not be gradual or uniform. The massive air movements and the heat transported from the day side would create complex patterns of freezing and thawing. Some areas might experience rapid freeze-thaw cycles as warm air masses from the day side periodically sweep across the night side, while other areas would become permanently frozen as they settle into their new role as Prephi, the cold side of our planet. The boundary between day and night would become a zone of incredible oceanic activity. Here, the hot waters from the day side would meet the cold waters from the night side, creating temperature gradients far steeper than anything in our current oceans. These gradients would drive powerful currents and create unique ecosystems adapted to the extreme conditions. Tides, one of the most familiar features of our oceans, would also change dramatically. Currently, tides are caused by the gravitational pull of the Moon and Sun as Earth rotates beneath them. With Earth no longer rotating, the Moon would hang motionless in the sky above one hemisphere, creating a permanent high tide on the side facing the Moon and a permanent low tide on the opposite side. But the Sun's gravitational effect would create a different pattern. As Earth continues its orbit around the Sun, the solar tide would slowly migrate around the planet over the course of a year, creating a slow annual cycle of rising and falling water levels that would be quite different from our familiar daily tides. The ocean floors themselves would not escape the transformation. The absence of Coriolis forces would change the patterns of sediment deposition, while the new current patterns would erode some areas and build up others in entirely new ways. Underwater mountain ranges might be exposed as currents carve new channels, while deep ocean basins might fill with sediments carried by the linear flows from dayside to nightside. Marine life would face challenges beyond imagination. The familiar migration patterns of whales, fish, and other sea creatures are often tied to ocean currents that would no longer exist. The complex food webs that depend on the mixing of nutrients by rotational currents would collapse, forcing marine ecosystems to adapt to entirely new patterns of nutrient distribution. The division of light and dark as Earth settles into its new state of motionless existence. One of the most profound changes would be the permanent division of our planet into hemispheres of eternal day and eternal night. This division would create two entirely different worlds on the same planet, each with its own unique characteristics and challenges. The day side would become a realm of perpetual brightness and increasing heat. Without the relief of night to allow cooling, temperatures would continue to rise until they reached an equilibrium between incoming solar energy and the energy radiated back to space. This equilibrium would be much hotter than any climate Earth has ever experienced. Picture vast deserts stretching across continents, their surfaces baked by a sun that never sets. The intense heat would create mirages that stretch to the horizon, making the landscape shimmer and dance in the eternal daylight. Rock formations would expand and contract with the daily temperature cycles caused by the sun's apparent movement across the sky. But without the relief of cooling nights, the average temperature would be far higher than anything in our current world. Water would become incredibly scarce on the day side. Most surface water would either evaporate into the atmosphere or flow toward the cooler night side. Rivers and lakes would dry up, leaving behind salt flats and mineral deposits that would create alien-looking landscapes. Only the deepest aquifers might retain some water, and even these would be under constant pressure from the heat above. Plant life on the day side would face an impossible challenge. The intense heat and lack of water would make photosynthesis difficult, while the constant daylight would disrupt the natural rhythms that many plants depend on. Some desert-adapted species might survive near the terminator line where conditions are more moderate, but most of the day side would become barren. The eternal brightness would create its own unique phenomena. Without the cycle of day and night, the light would have a different quality than we're used to. Shadows would move across the landscape as the sun traces its path across the sky. but they would follow the same pattern every day, creating permanent zones of relative shade and intense illumination. The night side would present an entirely different set of conditions. Plunged into permanent darkness, this hemisphere would begin a process of cooling that would continue until it reached equilibrium with the small amount of heat transported from the day side and the minimal warmth from Pemmican. Earth's core. In this realm of eternal night, temperatures would drop far below anything currently experienced on our planet. The absence of solar heating would allow the land and oceans to radiate their heat into space without replacement, creating conditions colder than the polar regions of today. Ice would become the dominant feature of the nightside landscape. Starting from the poles and the areas furthest from the terminator line, ice sheets would gradually expand, covering continents in glaciers kilometers thick. These ice sheets would be unlike those of our current ice ages because they would be permanent and would continue growing as long as the planet remained motionless. The eternal darkness would be broken only by the stars and the moon, when it's visible from the night side. But even the moon would behave differently. Instead of rising and setting each night, it would hang motionless in one part of the sky for weeks at a time as Earth orbited the Sun, then disappear for weeks before appearing in a different position. This permanent darkness would create unique atmospheric phenomena. Without solar heating to drive weather patterns, the night side would experience a different kind of meteorology. The cooling air would create high-pressure systems of enormous stability, but these would be disrupted by warm air flowing in from the day side, creating dramatic weather along the terminator line. Aurora displays would become more prominent on the night side, as the planet's magnetic field, if it still existed, would guide charged particles from the solar wind into the polar regions. These auroras might be visible across much larger areas of the night side due to the absence of light pollution and the changes in atmospheric circulation. The terminator line itself, the boundary between day and night, would become perhaps the most interesting region of our transformed planet. This twilight zone would experience conditions somewhere between the extremes of the two hemispheres. Here, the sun would hang perpetually at the horizon, creating a landscape of eternal sunrise or sunset. This boundary region would receive enough solar energy to prevent the extreme cooling of the night side, but not so much as to experience the scorching heat of the day side. It might become the only region where liquid water could exist stably on the surface, making it a potential refuge for life. The terminator line would also be a zone of constant weather activity. The meeting of hot air from the day side and cold air from the night side would create a perpetual storm system that circles the planet along this boundary. These storms would be unlike anything we've ever seen, fed by the enormous temperature differences and the constant flow of air between the two hemispheres. In this twilight zone, the landscape would be shaped by unique erosional patterns created by the constant wind and the dramatic temperature gradients. Valleys would be carved by the eternal winds, while the alternating heating and cooling at the boundary would create unique rock formations and mineral deposits. The collapse of Earth's magnetic shield, among the most consequential changes following Earth's sudden stop, would be the gradual weakening and eventual collapse of our planet's magnetic field. This invisible shield, which has protected life on Earth for billions of years, exists only because of the complex dynamics within our planet's core, dynamics that depend critically on Earth's rotation. Deep beneath our feet, about 3,000 kilometers below the surface, lies Earth's outer core, a layer of liquid iron and nickel heated to temperatures exceeding the surface of the Sun. This molten metal is in constant motion, driven by convection currents created by heat from the inner core and influenced by the Coriolis effect from Earth's rotation. The movement of this electrically conducting fluid creates electric currents, and these currents generate the magnetic field that extends far out into space around our planet. This process, called the geodynamo, requires the precise combination of a rotating planet and convecting molten metal in the core. When Earth suddenly stops rotating, the Coriolis effect that helps organize these currents disappears. Without this organizing force, the complex patterns of flow in the outer core would begin to break down. The convection would continue, driven by heat from the inner core, but it would no longer be organized into the patterns necessary to maintain a strong, stable magnetic field. The collapse would not be immediate. Earth's magnetic field has momentum of its own, and it would take months or possibly years for it to weaken significantly. But the process, once started, would be irreversible as long as the planet remained motionless. Picture the magnetic field lines that currently stretch from pole to pole, creating the protective envelope around our planet. As the geodynamo weakens, these field lines would become irregular and chaotic. The magnetic poles, which currently wander slowly around the geographic poles, would begin to move erratically. Multiple magnetic poles might appear and disappear as the field attempts to reorganize itself without the stabilizing influence of rotation. Eventually, Earth's magnetic field would become so weak and chaotic that it would no longer provide effective protection from the solar wind and cosmic radiation. Our planet would find itself naked before the harsh environment of space, exposed to radiation that had been deflected for billions of years. The solar wind, a stream of charged particles flowing constantly from the sun, would no longer be deflected around Earth by the magnetic field. Instead, these particles would strike our atmosphere directly, causing it to gradually erode away into space. This process, called atmospheric escape, occurs on planets without strong magnetic fields, like Mars. The high-energy particles from the solar wind would strip away the lighter elements in our atmosphere, particularly hydrogen and oxygen. Over long periods, this could lead to the loss of much of our atmosphere, including the water vapor that makes life possible. The process would be gradual but relentless, slowly transforming Earth into a world more like Mars, with a thin atmosphere unable to support liquid water on the surface. Cosmic radiation, those high-energy particles from distant stars and galaxies, would also reach Earth's surface without the protective magnetic field to deflect them. This radiation is far more dangerous to life than the solar wind, capable of damaging DNA and making survival difficult for most forms of life. The loss of magnetic protection would particularly affect the upper atmosphere and any life forms exposed to the surface. The increased radiation would make the day side even more hostile to life, while the night side would at least have the planet itself as a shield against radiation coming from the sun's direction. Satellites and any remaining electronic systems would face constant bombardment from charged particles, making them unreliable or completely inoperative. The modern technological world, dependent on satellite communications and GPS systems, would find these technologies gradually failing as the magnetic field weakens and space-based equipment is damaged by radiation. The aurora displays, those beautiful light shows created when solar wind particles interact with our magnetic field, would change dramatically. Instead of being confined to the polar regions by the organized magnetic field, auroras might appear anywhere on the night side as charged particles strike the atmosphere without being guided by magnetic field lines. But these auroras would be different from the ones we know. Without the organized magnetic field to channel the particles into familiar patterns, the light displays would be more chaotic and unpredictable. They might be brighter in some ways, as more particles would reach the atmosphere, but they would lack the structured beauty of current auroral displays. The Van Allen radiation belts, regions of charged particles trapped by Earth's magnetic field, would also disappear. These belts currently pose a hazard to spacecraft and astronauts venturing beyond low Earth orbit, but their disappearance would not necessarily make space travel safer. Without the magnetic field to trap and organize these particles, radiation levels throughout Earth's magnetosphere would become more uniform but potentially more dangerous. The transformation of seasons, and whether the concept of seasons, one of the fundamental rhythms of life on Earth, would be completely transformed in a world that no longer rotates. Our familiar cycle of spring, summer, fall, and winter exists because Earth's axis is tilted relative to its orbit around the Sun, causing different parts of the planet to receive varying amounts of solar energy throughout the year. In a non-rotating world, this seasonal progression would still occur, but it would manifest in entirely different ways. Instead of the gradual change from season to season that we experience as Earth rotates through its daily cycle, we would see seasonal changes as slow migrations of temperature zones across the planet's surface. Picture the summer solstice in the northern hemisphere of our rotating world. On a motionless Earth, this would mean that the Sun would hang highest in the sky above the Tropic of Cancer, creating a zone of maximum heating that would remain stationary relative to the ground. As Earth continued its orbital journey around the Sun, this zone of maximum heating would slowly migrate southward over the course of months, reaching the Tropic of Capricorn at what would have been the winter solstice. The day-night terminator line would also migrate with the seasons. During the equinoxes, this line would pass through both poles, dividing Earth into exact halves of day and night. But during the solstices, the terminator line would be tilted, creating a zone of permanent day that extends beyond one pole while leaving the other pole in permanent darkness. These seasonal migrations would create moving climate zones unlike anything in our current world. Areas that experience moderate temperatures during one part of the year would see these conditions slowly migrate away, to be replaced by either the intense heat of the direct sun or the cold of extended darkness. Weather patterns would be equally transformed. Currently, our weather systems are driven by the interaction of solar heating, Earth's rotation, and the distribution of land and sea. Without rotation, the fundamental drivers of weather would be the temperature differences between heated and cooled areas, modified by the slow seasonal migration of these zones. Imagine continental-scale weather systems that persist for months at a time, slowly shifting across the planet as the seasons change. Instead of the relatively rapid movement of storm systems that we see today, weather patterns would have a ponderous, almost geological quality to their movement. The monsoons, those seasonal wind patterns that bring life-giving rain to billions of people, would be completely altered. Currently, monsoons are driven by the seasonal heating and cooling of continents relative to oceans, combined with the Coriolis effect from Earth's rotation. Without rotation, monsoon patterns would become much simpler but also much more extreme, as the temperature differences between hot and cold regions would be far greater than anything we experience today. Hurricanes and typhoons, those powerful rotating storms that draw their energy from warm ocean waters, would not be able to form in their familiar spiral patterns without the Coriolis effect. Instead, we might see massive linear storm systems, like enormous squall lines that could stretch across entire continents, driven by the temperature differences between the day and night sides of our planet. The jet streams, those high-altitude rivers of fast-moving air that guide weather patterns around the globe, would disappear entirely. These streams exist because of the temperature difference between the equator and poles, organized by Earth's rotation into rivers of air that circle the planet. Without rotation, air movement would follow much simpler patterns, flowing directly from high-pressure to low-pressure areas without the curves and meanders that characterize current atmospheric circulation. Precipitation patterns would be revolutionized. Rain and snow would fall in entirely new patterns determined by the new air circulation patterns, rather than the familiar storm tracks we know today. Some regions might experience constant precipitation as they remain in zones where warm, moist air meets cold air, while others might never see rain again as they find themselves in permanently high-pressure areas or in the rain shadows of the new circulation patterns. The water cycle itself would be disrupted. Evaporation would be enormous on the hot day side, while precipitation would be concentrated along the terminator line and on the cold night side. This would create a massive transport of water from one side of the planet to the other, fundamentally altering the distribution of fresh water that all terrestrial life depends upon. Temperature records as we know them would become meaningless. Instead of daily highs and lows, seasonal averages and climate zones based on latitude, we would have permanently hot regions, permanently cold regions, and boundary zones where temperatures might vary dramatically as air masses from different thermal zones meet and interact. The growing seasons that agriculture depends on would be replaced by thermal zones that migrate slowly across the planet. Areas might experience months of growing weather, followed by months of conditions too hot or too cold for plant growth, creating agricultural challenges that would require completely new approaches to food production. The unraveling of ecosystems, the intricate web of life that has evolved on Earth over billions of years, has developed in response to the rhythms created by our planet's rotation. The sudden stop of this rotation would unravel these ecosystems in ways both immediate and gradual, as every living thing would be forced to adapt to conditions for which evolution had not prepared them. Consider first the plants, the foundation of most terrestrial ecosystems. Nearly all plant life has evolved complex internal clocks that respond to the cycle of day and night. These circadian rhythms control everything from when flowers open and close to when trees shed their leaves. Photosynthesis itself is optimized for the daily cycle of light and darkness that has been constant throughout evolutionary history. On the day side of our motionless planet, plants would face the unprecedented challenge of constant daylight combined with ever-increasing heat. Most plants require a period of darkness to complete essential biological processes, including the repair of photosynthetic machinery and the conversion of stored starches to energy. Without this dark period, many plants would experience photooxidative stress, where the constant light would actually damage their cellular machinery faster than it could be repaired. The intense heat on the day side would compound these problems. As temperatures rise far beyond what any terrestrial plant has evolved to handle, proteins would denature, cell membranes would become unstable, and the delicate biochemical processes of life would break down. Even desert plants, adapted to extreme heat, would find themselves overwhelmed by temperatures that never decrease and that continue to rise as the sun beats down relentlessly. Water stress would add another layer of challenge. With surface water evaporating rapidly and no rainfall patterns to replace it, even the most drought-adapted plants would struggle. The familiar strategies of desert survival, such as storing water in thick stems or deep root systems, would be insufficient against the relentless heat and aridity of the eternal day side. On the night side, plants would face different but equally challenging conditions. The permanent darkness would make photosynthesis impossible, forcing all plant life to either die or somehow survive on stored energy until that too was exhausted. The extreme cold would freeze the water within plant cells, rupturing cell walls and killing most vegetation within days or weeks. Some plants might survive near the terminator line, where they could receive enough light for photosynthesis while avoiding the extreme temperatures of either hemisphere. These twilight zones might become the last refuges for terrestrial plant life, creating narrow bands of vegetation that circle the planet along the boundary between day and night. Animal life would face equally severe challenges. Most animals have evolved migration patterns, feeding behaviors, and reproductive cycles that are tied to daily and seasonal rhythms. Birds that migrate thousands of miles following seasonal changes would find their navigation systems confused by the lack of familiar cues. The magnetic field that many species use for navigation would be weakening and becoming unreliable. On the day side, animals would face the immediate challenge of finding shelter from the intense heat and finding water in an increasingly arid landscape. Nocturnal animals would be particularly affected, as there would be no night to provide the cooler temperatures they need for activity. Diurnal animals might have some advantage initially, but as temperatures continued to rise, even they would struggle to survive. Hibernation and estivation, those survival strategies that allow animals to endure extreme conditions by reducing their metabolic rate, might become more important than ever. Animals capable of entering these dormant states might be able to survive longer in the harsh conditions of either hemisphere. The night side would become a frozen wasteland where most warm-blooded animals would struggle to maintain their body temperature. Only animals with extreme cold adaptations, like Arctic foxes or penguins, might have a chance of survival, and even they would face challenges as the cooling continued far beyond anything they had evolved to handle. Marine ecosystems would face their own set of disruptions. Ocean currents that currently distribute nutrients around the globe would be replaced by the new circulation patterns driven by temperature differences rather than rotation. Upwelling zones that bring deep, nutrient-rich water to the surface would shift or disappear entirely, starving the microscopic life that forms the foundation of marine food webs. Fish migrations would be disrupted as the ocean currents they follow disappear or change direction. Many fish species time their spawning to coincide with seasonal changes in water temperature or current patterns. With these familiar cues disrupted, reproduction could fail for entire species. Coral reefs, already stressed by current climate change, would face impossible conditions. The extreme heating on the day side would cause massive coral bleaching events, while the disruption of ocean currents would alter the nutrient flow that corals depend on. Even reefs in more moderate zones might struggle with the changed water chemistry and temperature patterns. The microscopic life that forms the base of most ecosystems would be among the first to be affected and among the most critical to the survival of larger organisms. Soil bacteria that fix nitrogen, making it available to plants, might be killed by extreme temperatures or disrupted by the changed conditions. Marine phytoplankton that produce much of Earth's oxygen might find their carefully evolved life cycles disrupted by the new ocean circulation patterns. Pollination networks would collapse as the insects, birds, and other animals that move pollen between plants would either die or find their behavioral patterns disrupted by the lack of familiar environmental cues. Many flowering plants depend on specific pollinators that have evolved to visit them at particular times of day or year. Without these relationships, plant reproduction would fail even for species that might otherwise survive the new conditions. Predator-prey relationships would be disrupted as animals found their hunting and feeding patterns no longer synchronized with the behavior of their prey. Nocturnal predators would struggle in permanent daylight, while animals that depend on seasonal abundance of food would find these predictable resources no longer available. Some organisms might find unexpected opportunities in this transformed world. Extremophiles, those organisms that thrive in conditions previously thought impossible for life might expand their ranges. Bacteria that can survive in boiling water or sub-freezing temperatures might find new niches to exploit. But these would be tiny oases of life in a world where the vast majority of species would face extinction. A world spinning slower to better understand the catastrophic nature of a complete stop. It's valuable to consider what would happen if Earth simply slowed down gradually rather than stopping entirely. This scenario, while still dramatic, would give us insight into how dependent our world is on the specific rate of rotation we currently experience. If Earth's rotation were to slow so that a day lasted 48 hours instead of 24, the changes would be significant but not immediately catastrophic. The longer days would mean longer periods of heating during daylight and longer periods of cooling at night, creating greater temperature extremes than we currently experience. Imagine summer days where temperatures continue to rise for 24 hours straight, reaching levels far higher than current records, followed by 24 hours of cooling that might bring temperatures down to levels more typical of winter nights. These extreme temperature swings would stress both natural ecosystems and human infrastructure in ways our current world rarely experiences. Weather patterns would shift as the longer heating and cooling cycles created different pressure systems. Storms might be more intense but less frequent, as the longer cycles would allow more energy to build up before being released. The familiar rhythm of daily weather changes would be replaced by a slower, more ponderous cycle that could make weather prediction even more challenging than it is today. Ocean currents would adjust to the new rotation rate, but they would still exist in recognizable forms. The Coriolis effect would be weaker, making these currents broader and less defined, but the basic circulation patterns would remain. Marine life would face challenges from the changed currents and the longer day-night cycles, but many species might be able to adapt over time. If we imagine even slower rotation, say a day lasting a week, the challenges would become more severe. Week-long periods of daylight would allow surface temperatures to rise to dangerous levels, while week-long nights would allow extensive cooling that could threaten agriculture and natural ecosystems. The temperature extremes would approach those of a tidally locked planet, where one side always faces the sun. Plants would struggle with week-long periods of continuous light, followed by week-long periods of darkness. Most plants require a regular cycle of light and dark for optimal health, and such extended periods of either condition would stress their biological processes. Some plants might adapt by changing their metabolic strategies, but many would likely not survive the transition. Animals would face similar challenges with week-long days and nights. Nocturnal animals would struggle during the extended daylight periods, while diurnal animals would find the week-long nights difficult to endure. Migration patterns would be disrupted as animals tried to adapt to the new timescales of environmental change. But even these scenarios, dramatic as they would be, pale in comparison to a complete stop. The key difference is that any rotation, no matter how slow, would maintain some of the fundamental systems that make Earth habitable. The geodynamo would continue to operate, though perhaps less efficiently, maintaining Earth's protective magnetic field. Ocean currents would still exist, distributing heat around the planet. Weather systems would still form and move, even if their patterns were altered. A complete stop, however, would eliminate these moderating influences entirely. Without any rotation, Earth would lose the physical processes that have maintained its habitability for billions of years. The planet would begin a transformation into something more like Venus or Mars, worlds where the absence or weakness of these processes has created environments hostile to life as we know it. The comparison helps us appreciate just how precisely balanced our current situation is. Earth's 24-hour rotation period is not arbitrary, but represents a sweet spot that maintains the complex systems necessary for life. Faster rotation would create stronger Coriolis effects and more extreme weather, while slower rotation would create temperature extremes and weaker magnetic fields. Our current rate represents billions of years of evolution toward a stable, life-supporting system. The tidal forces of a still world in our examination of a motionless Earth, we must consider how the gravitational forces that create our tides would behave in this transformed world. Currently, we experience 2 high tides and 2 low tides each day as Earth rotates beneath the tidal bulges created by the Moon's gravitational pull. In a world without rotation, this familiar rhythm would be replaced by something entirely different and far more dramatic. Picture the Moon hanging motionless in the sky above one hemisphere of our stationary planet. The gravitational force that currently creates our modest tides would now have unlimited time to work its influence on Earth's waters. Instead of the gentle rise and fall we're accustomed to, the Moon would gradually pull the oceans into a permanent configuration, with water levels highest on the side facing the Moon and lowest on the opposite side. This would not be a gentle process. The initial movement of water toward the Moon-facing side would create massive waves as the ocean attempted to redistribute itself according to the new gravitational reality. Imagine tsunamis larger than any in recorded history, but instead of being caused by earthquakes or underwater landslides, these would be caused by the Moon's relentless gravitational pull on a planet that no longer rotates away from its influence. The final configuration would be unlike anything we've ever seen. The Moon-facing hemisphere would experience a permanent high tide that could be hundreds of feet higher than current sea levels. Coastal cities on this side of the planet would find themselves either underwater or dealing with drastically altered coastlines as the oceans reshape themselves to match the gravitational forces. On the opposite side of Earth, the anti-Moon hemisphere, water levels would drop dramatically as the Moon's gravity pulled water away toward the other side of the planet. Ocean floors that had been underwater for millions of years would be exposed, revealing underwater mountain ranges, deep-sea trenches, and the remnants of ancient ecosystems preserved in the deep-sea sediments. The regions between these extremes, roughly along the great circle that passes through both poles and is perpendicular to the Moon-Earth line, would experience moderate water levels. But even these areas would see dramatic changes as the entire ocean circulation system adapted to the new gravitational configuration. Rivers would flow in new directions as the changed water levels altered the gradients that determine where water flows. Some rivers might reverse course entirely, while others might find their mouths hundreds of miles inland as the oceans retreat from their previous coastlines. The Amazon, the Nile, the Mississippi, and all the great rivers of the world would need to carve new paths to reach the transformed oceans. The Sun's gravitational influence would add another layer of complexity to this tidal reorganization. While weaker than the Moon's effect, the Sun's gravity would still influence the distribution of water on our motionless planet. As Earth continued its yearly orbit around the Sun, the solar tidal effect would slowly migrate around the planet, creating an annual cycle of rising and falling water levels that would be superimposed on the permanent lunar tide. During times when the Sun and Moon are on the same side of Earth, their gravitational effects would combine, creating even more extreme tidal bulges. When they are on opposite sides, their effects would partially cancel each other out, providing some relief from the extreme water level differences. The solid Earth itself would also respond to these tidal forces. Currently, the ground beneath our feet rises and falls by several inches each day due to tidal forces, but this effect is usually imperceptible because Earth rotates through it so quickly. On a motionless planet, the Moon's gravity would have time to deform the solid Earth more dramatically, creating permanent bulges in the planet's crust. This crustal deformation would trigger earthquakes as the rock adjusted to the new stress patterns. Fault lines around the world would experience forces they were never designed to handle, potentially triggering seismic activity far more intense than anything caused by normal tectonic processes. The combination of crustal deformation and massive water redistribution would alter Earth's moment of inertia, the distribution of mass around the planet's center. This would affect how our planet responds to gravitational forces from other bodies in the solar system, potentially altering Earth's orbit slightly over very long periods. Underground water systems would also be affected by the massive redistribution of surface water. Aquifers that currently provide fresh water to billions of people might drain toward the new ocean configurations, while other areas might find themselves with unexpected underground water sources as the changed surface conditions alter the flow of groundwater. The changed ocean levels would expose vast areas of seafloor while submerging coastal regions that have been above water for millions of years. This would create opportunities for new types of ecosystems to develop in the exposed areas, while destroying existing coastal and shallow water ecosystems in the submerged regions. Ice sheets and glaciers would also respond to the changed gravitational configuration. The massive redistribution of water around the planet would alter the gravitational field in ways that could affect ice flow patterns. Glaciers might accelerate their movement toward the new ocean configurations, while ice sheets might find their flow patterns altered by the changed gravitational landscape. Ancient stories and cosmic mythology throughout human history, cultures around the world have told stories of times when the sun stood still, when day and night were disrupted, or when the very foundations of the world, Kaf, were shaken. These ancient tales, found in mythologies from every continent, speak to a deep human awareness of our dependence on the cosmic cycles that govern our planet. In the biblical book of Joshua, we find the famous account of the sun standing still over Gibeon, allowing the Israelite army to complete their victory in the extended daylight. While interpreted by believers as divine intervention, such stories might also reflect ancient memories or fears of cosmic disruption, times when the familiar order of day and night was threatened or imagined to be threatened. The ancient Greeks told of Phaethon, son of Helios, who convinced his father to let him drive the chariot of the sun across the sky. Unable to control the powerful horses, Phaethon drove too close to Earth, scorching the land and creating deserts, before Zeus struck him down with a thunderbolt to prevent the destruction of the world. This myth captures the catastrophic potential of solar energy, unchecked by the regular patterns that normally govern day and night. Chinese mythology speaks of the 10 suns that once blazed in the sky simultaneously, creating unbearable heat that threatened all life on Earth. The hero Hu Yi shot down 9 of the suns with his bow, leaving only one to provide the gentle warmth necessary for life. This story, like many others, recognizes the delicate balance required for life to flourish and the catastrophic potential of that balance being disrupted. Norse mythology tells of Ragnarok, the twilight of the gods, when the sun and moon will be devoured by wolves, plunging the world into darkness before the final battle that will destroy and then remake the world. This apocalyptic vision includes the disruption of the cosmic order as a key element of the end times. The Hindu concept of cosmic cycles includes periods when the normal order of the universe is disrupted, when day and night cease their regular pattern, and when the very laws of nature are suspended. These stories suggest an ancient understanding that the stability we take for granted is not permanent, but depends on forces beyond human control. Indigenous cultures around the world have their own versions of these themes. Many Native American tribes tell stories of times when the sun refused to rise or set, creating either eternal day or eternal night until heroes or spirits could restore the proper order. These tales often emphasize the interconnectedness of all life and the importance of maintaining harmony with natural cycles. The Maori of New Zealand tell of Maui slowing the sun by lassoing it, forcing it to move more slowly across the sky to give humans more daylight for their work. While this story has a more positive outcome than most, it still deals with the theme of disrupting the natural order of day and night. Australian Aboriginal Dreamtime stories include accounts of the Sun Woman and Moon Man whose eternal dance across the sky creates the cycle of day and night. Some versions tell of times when this dance was disrupted, leading to chaos in the natural world until the proper rhythm could be restored. These stories from diverse cultures suggest that humans have long understood, at least intuitively, how dependent we are on the cosmic cycles that govern our planet. The fear of these cycles being disrupted appears to be universal, perhaps reflecting an evolutionary awareness of our fundamental dependence on the stability of day and night, the seasons, and the other rhythms that make life possible. Modern science has given us a much more detailed understanding of these dependencies, but the ancient stories remain relevant because they capture the emotional and existential significance of our relationship with cosmic forces. They remind us that the stability we take for granted is not guaranteed, and that our existence depends on the continuation of processes that operate on scales far beyond human influence. The recurring theme in these stories is often the restoration of order after a period of cosmic chaos. Heroes intervene, gods are appeased, or natural forces reassert themselves to return the world to its proper functioning. This reflects a deep human hope that even when the fundamental order of things is threatened, there are ways to restore balance and continue life. In our modern context, these ancient stories take on new meaning as we better understand the actual mechanisms that maintain Earth's habitability. While we now know that the sun standing still would not be a simple matter of divine intervention, but would require the cessation of Earth's rotation with all its catastrophic consequences, the ancient wisdom that recognized this as an ultimate threat to life remains valid. The stories also remind us that humans have always lived with the awareness that our existence depends on forces beyond our control. The cosmic cycles that govern day and night, the seasons, and the climate are not human creations, but natural processes that we have learned to live within. The ancient fear of these processes being disrupted reflects a realistic understanding of our place in the natural order. Science fiction visions the concept of Earth's rotation stopping or being dramatically altered has captured the imagination of science fiction writers for generations, inspiring stories that explore both the scientific consequences and the human drama of such an event. These fictional explorations often serve as thought experiments, allowing us to consider not just the physical changes that would occur, but how human society might respond to such a fundamental transformation of our world. One of the classic treatments of this theme is found in works that imagine Earth becoming tidally locked, with one side permanently facing the sun, while the other remains in eternal darkness. These stories often explore the development of distinct civilizations on each side of the planet, with the day-side inhabitants adapting to intense heat and eternal light, while the night-side dwellers learn to survive in breach, permanent cold and darkness. In these fictional worlds, the Terminator line, the boundary between day and night, often becomes a crucial setting. Writers have imagined mobile cities that travel along this boundary, staying in the zone of perpetual twilight where conditions remain moderate enough for human survival. These traveling settlements must constantly move to maintain their position relative to the sun, creating societies built around migration and adaptation. Some science fiction stories explore the technological solutions that advanced civilizations might develop to cope with a non-rotating world. Massive atmospheric processes might be built to maintain air circulation, while enormous solar collectors on the day side could beam energy to the night side through microwave transmission or other advanced technologies. These stories often grapple with the engineering challenges of maintaining habitability on a planet that no longer maintains itself through natural processes. The social and political implications of such a world have also been explored in fiction. Stories have imagined conflicts between the dayside and nightside populations, wars fought over the narrow habitable zones along the Terminator, and the breakdown of global civilization as different regions face vastly different survival challenges. Some authors have taken a more optimistic approach, imagining how such extreme conditions might drive human innovation and cooperation. Faced with the ultimate survival challenge, fictional human societies sometimes transcend their differences and work together to maintain habitability through technology and social organization. The psychological aspects of living in a world without day-night cycles have been explored in stories that consider how human consciousness and behavior might adapt to permanent day or permanent night. Characters in these stories often struggle with disrupted sleep patterns, seasonal affective disorders taken to extremes, and the challenge of maintaining mental health without the natural rhythms that humans have evolved to depend on. Time itself becomes a central theme in many of these stories. Without the natural cycle of day and night to mark the passage of time, human societies in these fictional worlds must create artificial timekeeping systems. Some stories explore how this might lead to the development of entirely different concepts of time and scheduling, with societies organizing themselves around temperature cycles or other environmental cues, rather than the missing solar rhythm. The theme of cosmic vulnerability is another common element in these science fiction explorations. Many stories use the stopped Earth scenario as a way to examine humanity's dependence on forces beyond our control and our potential for both destruction and adaptation when faced with ultimate challenges. Some authors have imagined that such an event might be caused by advanced alien technology, either as an attack on Earth or as an unintended consequence of some cosmic engineering project. These stories often explore themes of cosmic perspective, human insignificance in the face of advanced civilizations, and the fragility of our planetary environment. Other fictional treatments have focused on the immediate human drama of such an event. Stories might follow characters trying to survive the initial catastrophe, dealing with the collapse of infrastructure, the breakdown of social order, and the challenge of finding safety in a world suddenly transformed beyond recognition. The religious and philosophical implications of such an event have also been explored in science fiction. Some stories examine how different belief systems might interpret the stopping of Earth's rotation, whether as divine judgment, cosmic accident, or natural evolution. Characters in these stories often grapple with questions of meaning and purpose when faced with the apparent end of the world as they know it. Science fiction has also explored the possibility of reversing such a catastrophe. Stories have imagined the technological or even mystical means by which Earth's rotation might be restored, often requiring enormous sacrifices or the cooperation of all humanity. These stories typically focus on themes of hope, determination, and the human capacity to overcome seemingly impossible challenges. The genre has also used this scenario to explore environmental themes, drawing parallels between the catastrophic effects of stopping Earth's rotation and the more gradual but potentially equally devastating effects of climate change. These stories often serve as allegories for humanity's relationship with the natural environment and the consequences of disrupting natural systems. Through these various fictional explorations, science fiction has helped us imagine not just the physical consequences of such an event, but the full range of human responses it might provoke. These stories serve as thought experiments that can help us better appreciate the delicate balance that makes our current world possible and the importance of protecting the natural systems that sustain life on Earth. The ripple effects through the solar system, the sudden cessation of Earth's rotation would not occur in isolation, but would create subtle yet significant effects that would ripple outward through our solar system, altering the delicate gravitational dance that has maintained orbital stability for billions of years. Earth's rotation contributes to the planet's overall angular momentum, and any change to this rotation would slightly alter how our planet interacts gravitationally with other bodies in the solar system. While these effects would be small compared to the catastrophic changes on Earth's surface, they would accumulate over time and could lead to measurable changes in orbital mechanics. The most immediate effect would be on the Moon, our closest celestial neighbor. The Moon's orbit is gradually expanding due to tidal forces that transfer angular momentum from Earth's rotation to the Moon's orbital motion. If Earth suddenly stopped rotating, this transfer would cease and the Moon's orbital evolution would be fundamentally altered. Currently, the Moon is moving away from Earth at about 3.8 centimeters per year as tidal friction gradually slows Earth's rotation and speeds up the Moon's orbit. With Earth's rotation stopped, this process would halt and the Moon would remain at its current distance rather than continuing its slow spiral outward. Over geological timescales, this would result in a Moon significantly closer to Earth than it would have been if our planet had continued rotating normally. The changed relationship between Earth and Moon would also affect the stability of Earth's axial tilt. Currently, the Moon's gravitational influence helps stabilize Earth's rotation axis, preventing the chaotic tumbling that affects planets like Mars. Without rotation, this stabilizing effect would be lost, potentially making Earth more susceptible to gravitational perturbations from other planets that could alter its orientation in space. Earth's orbital motion around the Sun would also be subtly affected. The distribution of mass within a rotating planet is slightly different from that of a non-rotating planet due to the centrifugal force that creates Earth's equatorial bulge. When rotation stops, this bulge would gradually flatten as the planet adjusts to its new configuration, slightly altering Earth's moment of inertia and potentially affecting its orbital characteristics. These changes would be extraordinarily small, but in the precise clockwork of celestial mechanics, even tiny alterations can accumulate over millions of years to produce significant effects. Computer models of solar system evolution would need to be recalculated to account for a non-rotating Earth and its altered gravitational signature. The other planets in our solar system would also experience minute changes in their orbital dynamics. The gravitational influence between planets, while small compared to the Sun's influence, is precisely balanced to maintain the current orbital configurations. Any change to one planet's characteristics can propagate through the system, causing slight alterations in the orbits of other planets over very long timescales. Jupiter, with its enormous mass and complex system of moons, might be particularly sensitive to changes in the inner solar system's dynamics. The intricate gravitational relationships between Jupiter's major moons, known as orbital resonances, have remained stable for billions of years. While the effects of Earth's changed rotation would be extremely small at Jupiter's distance, the possibility exists that such changes could accumulate over geological time to affect even these distant kamei. Relationships. The asteroid belt, That region of rocky debris between Mars and Jupiter is also maintained in its current configuration by a delicate balance of gravitational forces. Changes to Earth's gravitational influence, while tiny, could theoretically alter the long-term evolution of asteroid orbits, potentially affecting the rate at which asteroids are deflected into Earth-crossing orbits. Perhaps most intriguingly, the change in Earth's rotation could affect the planet's interaction with the solar wind, the stream of charged particles flowing from the Sun. Earth's magnetosphere, assuming it survives the initial disruption caused by the cessation of rotation, would have a different orientation and behavior without the organizing influence of planetary rotation. This could alter how Earth's magnetosphere interacts with the interplanetary magnetic field carried by the solar wind. These interactions between planetary magnetospheres and the solar wind are part of the larger electromagnetic environment of the solar system. Changes to Earth's magnetic field behavior could potentially influence space weather patterns that affect other planets, particularly those with their own magnetic fields like Jupiter and Saturn. The long-term stability of the inner solar system has been maintained for billions of years through a complex web of gravitational relationships. While Earth's stopped rotation would not immediately threaten this stability, it would introduce a new variable into the system that could have unpredictable consequences over the vast timescales on which planetary systems evolve. Computer simulations of solar system dynamics typically assume that planetary characteristics remain constant over time, but the reality is that planets do evolve, and these changes can influence the entire primal system. Earth's rotation has been slowing throughout its history due to tidal friction with the Moon, and this gradual change has been factored into our understanding of solar system evolution. A sudden stop would represent a discontinuous change that would require entirely new calculations. The study of exoplanetary systems has revealed that planetary configurations can be quite diverse, with some systems showing evidence of past instabilities that dramatically rearranged planetary orbits. While our solar system has remained stable for billions of years, the sudden change in Earth's characteristics might provide insights into how planetary systems respond to disruptions. From a broader cosmic perspective, these ripple effects remind us that Earth is not an isolated world, but an integral part of a larger gravitational system. Our planet's rotation is not just important for maintaining life on Earth's surface, but is also part of the complex mechanics that maintain the stability of our entire solar system. The search for new equilibrium in the aftermath of Earth's rotational halt, our planet would begin a long journey toward a new state of equilibrium, a process that could take thousands or even millions of years as natural systems adapted to the transformed conditions. This search for balance would involve the redistribution of mass, energy, and momentum on a global scale, fundamentally reshaping every aspect of our planet's environment. The atmosphere would be among the first systems to begin this adjustment process. The initial chaotic winds and extreme weather would gradually give way to a simpler but still dramatic circulation pattern, driven primarily by the temperature difference between the day and night hemispheres. Over time, this circulation would become more organized and predictable, though it would remain far more extreme than anything in our current world. The new atmospheric circulation would establish persistent pressure systems unlike any we've seen before. The day side would develop a massive low-pressure system as hot air continuously rises from the superheated surface. This low-pressure zone would draw air from the night side, creating steady, strong winds flowing from the cold hemisphere toward the hot hemisphere at low altitudes. High in the atmosphere, the reverse flow would occur as hot air from the day side spreads outward and flows toward the night side, where it would cool and descend, creating a simple but powerful convection cell that encompasses the entire planet. This global circulation pattern would be far more organized than our current weather systems, but also far more extreme in its effects. The oceans would undergo their own process of adjustment as they sought a new equilibrium between the competing forces of solar heating, gravitational tides, and atmospheric circulation. The initial chaotic movement of water would eventually settle into more predictable patterns, though the final configuration would be unlike any ocean system in Earth's history. Ocean temperatures would stratify in new ways as the extreme heating on one side and cooling on the other created temperature gradients far steeper than anything in our current world. The boundary between hot and cold water masses would create zones of intense current activity as the different density water masses sought to mix and find equilibrium. Deep ocean circulation, currently driven by temperature and salinity differences created by global circulation patterns, would reorganize around the new thermal structure. Cold, dense water from the night side would sink and flow along the ocean floor toward the day side, while hot, less dense water from the day side would flow at the surface toward the night side, creating a simple but powerful thermohaline circulation. The redistribution of water due to tidal forces would also reach equilibrium as the oceans adjusted to their new configuration under the unchanging gravitational influence of the Moon and Sun. This process might take centuries as water slowly moved to match the gravitational potential, creating new coastlines and exposing or submerging vast areas of land. Ice sheets on the night side would continue growing until they reached a balance between the accumulation of ice from precipitation and atmospheric transport of moisture from the day side, and the slow melting at their edges where they contact slightly warmer zones. These ice sheets could become enormous, potentially covering entire continents in glaciers kilometers thick. The growing ice sheets would affect global sea level, potentially lowering ocean levels significantly as vast amounts of water became locked up in ice. This would expose more land area, particularly on the day side, where the combination of lower sea levels and the retreat of water toward the moon-facing hemisphere would reveal new landscapes. Plant and animal life would also seek new equilibriums, though this process would be marked by widespread extinction and the evolution of entirely new species adapted to the extreme conditions. Life might concentrate in narrow zones along the terminator line where conditions remain moderate enough for biological processes to continue. These terminator ecosystems would likely be unlike anything in Earth's current biosphere. Plants might evolve to take advantage of the constant angle of sunlight, developing new photosynthetic strategies optimized for twilight conditions. Animals might develop new behavioral patterns adapted to the unchanging light levels and the constant winds flowing between the day and night sides. Some extremophile organisms might expand their ranges to colonize the harsh conditions of the day and night sides. Heat-loving bacteria might thrive in the hot springs and geothermal areas of the day side, while cold-adapted microorganisms might find new niches in the growing ice sheets of the night side. The carbon cycle would establish new patterns as the distribution of plant life, ocean circulation, and atmospheric chemistry changed. Carbon dioxide levels might fluctuate dramatically as the planet's vegetation died off and decomposed, while the changed ocean circulation altered the ocean's ability to absorb and store carbon. Rock weathering patterns would change as the new climate zones established different temperature and precipitation patterns around the globe. The intense heat and aridity of the day side would slow chemical weathering, while the cold conditions of the night side would freeze most weathering processes. The most active weathering might occur along the terminator zone where liquid water and moderate temperatures could sustain chemical processes. Volcanic and tectonic activity would eventually adjust to the new stress patterns created by the changed distribution of mass and the altered tidal forces. New patterns of earthquakes and volcanic eruptions might emerge as the planet's crust found new ways to release the stresses created by the transformed surface conditions. The magnetic field, if it could regenerate after the initial collapse, might eventually find a new configuration based on whatever convection patterns could be maintained in the core without the urbanizing influence of tassel. Rotation. This new magnetic field would likely be much weaker and less stable than our current field, providing limited protection from cosmic radiation. Over geological timescales, even more fundamental changes might occur. The altered climate and ice distribution could affect the planet's rotation axis through changes in the distribution of mass. The growth of enormous ice sheets could shift Earth's center of mass enough to alter the planet's orientation in space, creating new patterns of seasonal heating as the planet continued its orbit around the Sun. The evolution toward equilibrium would be a process of trial and error on a planetary scale, with each system affecting every other system in complex feedback loops. What emerges after millions of years might be a planet that is stable in its new configuration, but utterly alien compared to the Earth we know today. This new equilibrium, when finally reached, would represent a completely different kind of world, one where life, if it survives at all, would exist in forms and patterns that we can barely imagine. It would be a world that demonstrates both the resilience of natural systems to find balance even under extreme conditions and the fundamental importance of the rotation that currently makes our planet a haven for life. The delicate dance of forces as we reach the end of our journey through this transformed world, we return to a fundamental truth about our planet. Earth's rotation is not merely a physical characteristic, but the conductor of an intricate symphony of forces that make life possible. Every breath we take, every drop of rain that falls, every gentle breeze that rustles through the leaves, exists because our planet maintains its ancient dance through space. The scenarios we have explored reveal the countless ways that rotation influences every aspect of our world. From the grand circulation of the oceans to the microscopic timing of cellular processes in plants and animals, the effect of Earth's spin permeates every level of existence. It shapes our weather, drives our magnetic field, organizes our ecosystems, and even influences the flow of time as we experience it. Consider the elegant complexity of the systems that rotation makes possible. The Coriolis effect, seemingly simple in its basic physics, creates the swirling storms that bring life-giving rain to distant continents. The tidal forces that arise from our spinning planet's interaction with the Moon create the intertidal zones where some scientists believe life first emerged from the sea. The day-night cycle regulates the biological clocks that synchronize all life on Earth to the rhythm of our rotating world. Yet this complexity emerges from something as fundamental as angular momentum, a property that our planet acquired billions of years ago from the swirling cloud of dust and gas that became our solar system. That ancient motion, preserved through eons of cosmic evolution, continues to shape every moment of our existence today. The thought experiment of a motionless Earth illuminates how precisely balanced our current world truly is. The speed of rotation is neither too fast nor too slow, creating days that are long enough for complex weather systems to develop but short enough to prevent extreme temperature variations. The tilt of our axis creates seasons that drive the migrations and life cycles that define our biosphere. The strength of our magnetic field, dependent on rotation, provides just enough protection from cosmic radiation without being so strong as to trap harmful particles. This balance did not arise by design but through billions of years of evolution and cosmic accident. Yet the result is a world so finely tuned for life that even small changes to fundamental parameters like rotation speed could have dramatic consequences for habitability. We live in what scientists sometimes call the Goldilocks zone, not just in terms of our distance from the Sun, but in terms of countless other variables that must be just right for life to flourish. The ancient stories that imagined the Sun standing still or the Earth ceasing its motion understood, perhaps better than they knew, that such events would represent the end of the world as we know it. While the storytellers of old could not have imagined the scientific details of magnetic field collapse or atmospheric circulation patterns, they grasped the essential truth that the cosmic order we depend on is both Dembema, powerful and fragile. Modern science has given us the tools to understand the mechanisms behind this cosmic order, but it has also revealed just how remarkable our situation truly is. Among the thousands of exoplanets now known to science, Earth remains unique in its combination of characteristics that support complex life. Our rotation rate, our magnetic field strength, our atmospheric composition, our distance from the Sun, and countless other factors all fall within narrow ranges that permit the existence of the intricate web of life we see around us. This understanding brings with it a profound sense of responsibility. We are the inheritors of a world shaped by 4.5 billion years of cosmic evolution, a world where countless random events and gradual changes have combined to create conditions of extraordinary complexity and beauty. The systems that maintain this world operate on scales far beyond human influence, yet we have developed the power to affect many of the delicate balances that these systems maintain. Climate change, pollution, habitat destruction, and other human activities represent our first serious attempt to modify planetary systems that have operated unchanged for millions of years. While we cannot stop Earth's rotation or dramatically alter its magnetic field, we can and do affect the atmospheric composition, ocean chemistry, and biological diversity that depend on these fundamental cosmic forces. The vision of a motionless Earth serves as a reminder of what we have to lose. Every ecosystem, every species, every beautiful landscape exists within the narrow envelope of conditions that Earth's rotation helps to maintain. The thunderstorms that water our crops, the ocean currents that moderate our climate, the magnetic field that protects us from harmful radiation, all depend on the continued spinning of our planet through space. But this vision also reminds us of the resilience and adaptability of natural systems. Even in our most extreme scenario, life might find ways to persist in the narrow zones where conditions permit survival. The history of life on Earth is a story of adaptation to changing conditions, of species that found ways to thrive even as their world transformed around them. Yet resilience has its limits, and the conditions that would follow the cessation of Earth's rotation would push those limits far beyond anything life has previously faced. The gradual changes that evolution can adapt to over millions of years are very different from the catastrophic, instantaneous changes that would follow a rotational halt. This brings us to a deeper appreciation of the present moment and the world we currently inhabit. The sunrise that greets us each morning, the sunset that closes each day, the changing seasons that mark the passage of time, all exist because our planet continues its ancient rotation. The familiar rhythms of day and night, the predictable patterns of weather and climate, the stable conditions that allow forests to grow and rivers to flow, all depend on forces that operate far beyond human control but that have remained constant throughout human history. In contemplating a world without rotation, we gain a new perspective on the world with rotation that we actually inhabit. Every aspect of our environment that we take for granted reveals itself as part of an intricate, interconnected system maintained by the simple fact that our planet spins. The air we breathe has been circulated around the globe by rotational forces. The water we drink has been part of weather systems driven by the Coriolis effect. The soil that grows our food has been enriched by climatic patterns that depend on the day-night cycle. Even the evolution of human consciousness and culture has been shaped by the rhythms that rotation creates. Our concepts of time, our sleep patterns, our seasonal celebrations, our navigation techniques, and our understanding of the cosmos all developed in response to the cycles created by our spinning planet. In losing rotation, we would lose not just the physical conditions that support life, but many of the temporal and spatial frameworks that make human culture possible. The thought experiment ultimately returns us to a sense of wonder at the delicate dance of forces that makes our world possible. In an universe that seems largely hostile to life, where planets are either frozen balls of rock or scorching gas giants, Earth maintains the precise conditions necessary for the extraordinary complexity we see around us. This is not a permanent guarantee, but an ongoing balance that has persisted for billions of years, and that we hope will continue for billions more. As we close our exploration of this transformed world, we are reminded that the greatest discoveries often come not from examining what is, but from imagining what might be. In envisioning a motionless Earth, we have learned to see our rotating Earth with new eyes, to appreciate the countless subtle forces that maintain the world we know, and to understand our place within the vast cosmic systems that sustain all life. The microscopic symphony. To truly understand the profound nature of Earth's rotation, we must venture into the realm of the infinitesimally small, where the effects of our planet's spin influence processes of the NC, molecular and cellular level. Here, in the hidden world of biology and chemistry, the rhythm of rotation orchestrates symphonies of life that we rarely consider yet depend upon for our very existence. Consider the circadian rhythms that govern nearly every living organism on Earth. These internal biological clocks, refined over billions of years of evolution, synchronize the biochemical processes of life to the 24-hour cycle created by our planet's rotation. In plants, these rhythms control when photosynthesis reaches its peak efficiency, when cells divide, and when flowers open to attract pollinators. The molecular machinery that drives these rhythms is extraordinarily complex. Deep within plant cells, protein complexes act as biological timepieces, their interactions oscillating with a period that matches Earth's rotational cycle. These molecular clocks can maintain their rhythm even in constant laboratory conditions, demonstrating how deeply the rotation cycle has been embedded in the very fabric of life. In a world without rotation, these ancient timepieces would lose their reference point. Plants that have evolved to optimize their energy production for specific times of day would find their internal programming mismatched to external reality. Flowers that open at dawn to catch early morning pollinators would open into eternal midday heat or eternal midnight cold, disrupting pollination networks that have existed for millions of years. The cellular processes of photosynthesis itself would be challenged in ways that extend far beyond the obvious problems of heat and light availability. The enzyme complexes that capture solar energy and convert carbon dioxide into sugars operate most efficiently within narrow temperature ranges and under specific light conditions. The constant heat of the day side would denature these proteins faster than cells could replace them, while the eternal cold of the night side would slow these reactions to a halt. Even more fundamentally, the process of cellular respiration, which releases energy from stored sugars, operates on cycles that are synchronized to the day-night rhythm. Cells throughout the plant kingdom have evolved to burn energy at different rates during different parts of the daily cycle, conserving resources during the cool night hours and ramping up activity during the warm day hours. Without this rhythm, plants would need to completely reorganize their energy management strategies. Animal physiology would face equally profound disruptions at the cellular level. The human body contains trillions of cells, each containing molecular clocks that synchronize to the light-dark cycle. These clocks control when hormones are released, when DNA repair processes are most active, and when cell division occurs. The disruption of these rhythms, even in our current world, leads to health problems ranging from insomnia to increased cancer risk. In a world of eternal day or eternal night, these cellular clocks would gradually drift out of synchronization, each cell following its own internal rhythm without the external cues that normally keep them coordinated. The result would be a kind of biological chaos where different parts of the same organism would be operating on different schedules, leading to physiological stress and eventual system failure. The immune system, which depends on carefully timed responses to threats, would be particularly vulnerable. Many immune functions follow circadian rhythms, with inflammation responses peaking at certain times of day and wound healing proceeding faster during specific hours. Without the organizing influence of the day-night cycle, immune responses might become chaotic and ineffective, leaving organisms vulnerable to diseases that they could normally fight off. Temperature regulation in warm-blooded animals depends not just on external temperature, but on internal rhythms that prepare the body for the thermal challenges of different times of day. Birds and mammals have evolved complex physiological mechanisms that anticipate temperature changes and adjust metabolic rates accordingly. These mechanisms would be severely disrupted by the extreme and constant temperatures of a non-rotating world. Even at the genetic level, the effects of rotation reach deep into the molecular structure of life. Gene expression, the process by which cells read their DNA instructions and produce proteins, follows circadian rhythms. Thousands of genes in every organism are activated and deactivated on schedules that match the rotation of Earth, ensuring that the right proteins are produced at the right times. This genetic choreography extends to DNA repair mechanisms, which are most active during certain parts of the daily cycle when cells are less busy with other activities. The timing of cell division is also carefully controlled, with most cell types dividing during specific windows of the circadian cycle. In a world without rotation, this genetic timing system would lose its coordination, potentially leading to increased mutation rates and cellular dysfunction. The water cycle, fundamental to all life, operates through processes that depend on molecular-level interactions affected by temperature and pressure cycles. The evaporation of water from plant leaves, called transpiration, follows daily rhythms that help plants conserve water during the hottest parts of the day. The molecular pumps that move water through plant tissues are regulated by circadian clocks, optimizing water transport for the environmental conditions that normally occur at different times of day. In animals, water balance is maintained through kidney function that varies throughout the day, producing more concentrated urine during sleeping hours to conserve water. The molecular mechanisms that control this process are synchronized to circadian rhythms, ensuring that animals maintain proper hydration while minimizing water loss during vulnerable periods. The chemistry of soil itself is influenced by daily temperature cycles, that affect the activity of microorganisms responsible for nutrient cycling. Bacteria that fix nitrogen from the atmosphere, making it available to plants, follow rhythms that are coordinated with plant uptake cycles. The molecular processes that break down organic matter and release nutrients operate most efficiently within specific temperature ranges that normally occur during particular times of day. In the oceans, microscopic phytoplankton that form the base of marine food webs synchronize their photosynthesis and cell division to daily light cycles. These tiny organisms produce much of the oxygen in our atmosphere and absorb enormous amounts of carbon dioxide, making them crucial to global climate regulation. Their molecular clocks coordinate these processes with the daily availability of sunlight, optimizing their energy production and reproduction. The disruption of these microscopic rhythms would cascade upward through entire ecosystems. Marine food webs depend on the predictable timing of phytoplankton blooms, which provide food for small animals that in turn feed larger predators. Without the organizing influence of daily light cycles, these blooms might become erratic or fail entirely, collapsing food webs that support billions of marine organisms. Even the atmosphere itself is influenced by molecular-level processes that follow daily rhythms. The photochemical reactions that break down pollutants and maintain atmospheric chemistry operate at rates that vary with temperature and light levels. Many of these reactions are most active during daylight hours when solar energy is available to drive chemical processes. In a world of eternal day and night hemispheres, atmospheric chemistry would reorganize around entirely different patterns, potentially leading to the accumulation of toxic compounds in some regions and the depletion of essential atmospheric components in others. The magnetic field that protects us from cosmic radiation influences biological processes at the molecular level in ways that scientists are only beginning to understand. Some migratory animals appear to sense magnetic fields through quantum mechanical processes in specialized proteins in their eyes. Birds, sea turtles, and other navigating animals rely on these molecular compasses to find their way across vast distances. The weakening and eventual collapse of Earth's magnetic field would disrupt these navigation systems, leaving these animals unable to complete migrations that are essential for their survival and reproduction. At the most fundamental level, the spin of Earth influences the behavior of fluids at the molecular scale through the Coriolis effect. While this effect is too small to influence the drainage of bathtubs, as is often claimed, it does affect large-scale fluid movements, including the circulation of fluids within living organisms. The movement of blood through the circulatory systems of large animals, the flow of sap through the vascular systems of tall trees, and the circulation of fluids within cells all occur within the context of Earth's rotation. These biological fluid dynamics have evolved over millions of years within the gentle influence of rotational forces. While the effects are subtle, they contribute to the overall efficiency of circulation systems that must move fluids against gravity and through complex networks of vessels and channels. The sudden absence of these forces might not immediately stop circulation, but it could affect the efficiency of fluid transport in ways that compound other stresses on biological systems. The crystalline structures that form the shells, bones, and other hard parts of living organisms also develop under the influence of gravitational and rotational forces. The orientation of calcium carbonate crystals in seashells, the alignment of collagen fibers in bone, and the structure of plant cell walls all form within the physical environment created by Earth's rotation. Changes to this environment could affect the mechanical properties of these biological materials, potentially making them weaker or less well adapted to the stresses they normally encounter. Even the process of evolution itself operates within the framework of rotational cycles. Natural selection has favored organisms that can synchronize their activities to daily and seasonal rhythms, leading to the complex biological clocks that govern life today. Genetic mutations that disrupt these timing mechanisms are usually disadvantageous, while mutations that improve synchronization with environmental cycles are favored by natural selection. In a world without rotation, the selective pressures that have shaped life for billions of years would suddenly change. Organisms with strong circadian rhythms might find themselves at a disadvantage, while those capable of operating without external timing cues might have an advantage. However, the vast majority of life forms are so deeply adapted to rotational cycles that few would be able to survive the transition to a non-rotating world. The molecular symphony of life plays out in countless other ways that depend on the reliable rhythms created by Earth's rotation. From the timing of hormone production to the coordination of cellular repair processes, from the regulation of gene expression to the synchronization of reproductive cycles, the molecular machinery of life has been fine-tuned over eons to operate within the framework of a rotating world. The atmospheric rivers of a changed world as our motionless Earth settles into its new reality. The atmosphere would develop circulation patterns unlike anything in the planet's history, creating vast rivers of air that would reshape weather and climate in ways both subtle and dramatic. These atmospheric rivers would become the arteries of our transformed world, carrying heat, moisture, and energy across a planet no longer governed by the familiar dynamics of rotation. The fundamental driver of these new circulation patterns would be the enormous temperature difference between the perpetually heated day side and the perpetually cooled night side. This temperature gradient would create pressure differences that dwarf anything in our current atmosphere, driving winds of incredible strength and persistence across the boundary between the two hemispheres. Imagine the day side as a vast continental-scale low pressure system, where the intense solar heating creates a massive updraft that draws air from thousands of miles away. The heated air would rise to great altitudes, forming towering columns of ascending air that could reach far into the stratosphere. These thermal towers would be unlike any weather phenomenon we currently know, persistent features that remain in the same location relative to the sun, growing stronger during the local waltz. Noon, when the sun reaches its highest point, and weakening but never disappearing during the local morning and evening. The rising air on the day side would create a vacuum effect, drawing cooler air from the night side across the terminator line in a vast planetary-scale wind system. These winds would be remarkably steady and predictable, flowing like a river from the high-pressure areas of the cold night side toward the low-pressure areas of the hot day side. The speed and volume of this air movement would be far greater than any wind system on our current planet. As the air crosses from night to day, it would encounter increasingly intense heating, causing it to expand and accelerate its upward movement. The transition zone, where cool night-side air meets the intense heating of the day side, would become a region of spectacular meteorological activity. Here, the rapid heating of cool air would create powerful convective currents, forming thunderstorms of unprecedented scale and intensity. These terminator storms would be persistent features of our transformed world, fed by the constant flow of cool air into hot regions and the unlimited energy available from the temperature difference. Unlike the thunderstorms we know today, which form and dissipate over hours or days, these storms would persist as long as the sun continued to shine on the day side, creating a ring of perpetual severe weather around the planet along the day-night boundary. The storms would be unlike anything in our current meteorology. Fed by unlimited moisture from the evaporation occurring on the day side, and unlimited energy from the temperature gradient, they could produce rainfall rates that exceed the most intense storms ever recorded. The latent heat released by this massive precipitation would add even more energy to the system, creating a feedback loop that would maintain the intensity of these perpetual storms. High in the atmosphere, the heated air from the day side would spread outward in all directions, flowing toward the night side in vast, high-altitude rivers. This upper-level flow would be the return circulation for the low-level winds flowing from night to day, completing a global convection cell that encompasses the entire planet. The scale of this circulation would be unprecedented, with air traveling thousands of miles from where it rises on the day side to where it descends on the night side. As this high-altitude air moves toward the night side, it would gradually cool, becoming denser and beginning to descend. The descent would accelerate as the air encounters the increasingly cold conditions of the night side, creating powerful downward currents that would compress and further cool the air as it approaches the surface. The night side would thus become a region of persistent high pressure, where the cooling air creates downward winds that suppress cloud formation and create clear but intensely cold conditions. This high-pressure system would be remarkably stable, fed by the constant flow of air from the day side and maintained by the continuous cooling that occurs in the absence of solar heating. The boundary between the ascending air on the day side and the descending air on the night side would create a global front, a zone of intense weather activity that circles the planet along the terminator line. This front would be far more persistent and intense than any weather front in our current world, creating a band of storms, clouds, and precipitation that would be visible from space as a bright ring around the planet. The three-dimensional structure of this global circulation would create unique weather patterns at different altitudes. Near the surface, the flow would be dominated by the movement of air from the high-pressure night side toward the low-pressure day side. In the middle atmosphere, the flow would be more complex, with some air continuing toward the day side while other air masses begin to rise in preparation for the return flow to the night side. In the upper atmosphere, the flow would be predominantly from day side to night side, carrying heat and moisture from the hot hemisphere toward the cold hemisphere. This upper-level flow would be remarkably steady and predictable, creating jet stream-like currents but with much greater speed and persistence than our current jet streams. The interaction between these different layers of atmospheric flow would create unique weather phenomena. Wind shear, the difference in wind speed and direction at different altitudes, would be extreme throughout much of the atmosphere. This shear would create turbulence and mixing that could generate weather patterns unlike anything we currently understand. Clouds would form in entirely new configurations within this transformed atmospheric circulation. On the day side, the intense heating would drive powerful convective currents that could create thunderheads reaching far higher into the atmosphere than any clouds in our current world. These massive storm systems would be fed by the unlimited moisture available from the evaporation of surface water and would be sustained by the continuous heating from the sun. The cloud formations would likely be organized into patterns that reflect the underlying circulation. Bands of clouds might form along the flow lines of the atmospheric rivers, creating striped patterns visible from space. The terminator zone would be marked by a nearly continuous band of storm clouds, while the night side might be largely clear as the descending air suppresses cloud formation. Precipitation patterns would be equally unique. The day side would experience intense evaporation, but might see relatively little precipitation, except near the terminator zone, where the rising air would cool and release its moisture. The night side would receive precipitation from the air masses flowing in from the day side, but this precipitation would likely be in the form of snow or ice due to the cold temperatures. The terminator zone would experience the most intense precipitation, as the warm, moist air from the day side would be forced to rise rapidly as it encounters the cooler air from the night side. This precipitation could take many forms, from intense rainfall to large hail, depending on the specific temperature and wind conditions at different locations along the boundary. The atmospheric pressure variations created by this global circulation would be far more extreme than anything we experience today. The low-pressure area on the day side could reach pressures well below any natural low-pressure system in our current world, while the high-pressure area on the night side could exceed the strongest high-pressure systems we currently know. These extreme pressure differences would drive winds that could reach speeds far exceeding any recorded on Earth today. The pressure gradient between the day and night sides would create a force that would accelerate air to incredible velocities as it flows from the high-pressure night side toward the low-pressure day side. The constant high-speed winds would have profound effects on the landscape. Erosion would occur at rates far exceeding anything in Earth's current environment, carving new valleys and reshaping mountains over relatively short geological timescales. The persistent winds would also transport enormous amounts of dust and debris, potentially burying some landscapes while exposing others. The atmospheric chemistry would also be affected by these new circulation patterns. The rapid transport of air masses between vastly different temperature zones would create chemical reactions that don't occur in our current atmosphere. The intense heating on the day side might drive photochemical reactions that produce new atmospheric compounds, while the extreme cooling on the night side might cause other compounds to condense out of the atmosphere entirely. Oxygen and carbon dioxide levels might vary significantly between the day and night sides as the different temperature and pressure conditions affect the solubility of gases and the rates of chemical reactions. Plants and animals that survive in this transformed world would need to adapt not only to the extreme temperatures and constant winds, but also to atmospheric compositions that might vary dramatically from place to barn. Place. The global atmospheric circulation would also affect the planet's energy balance in complex ways. The transport of heat from the day side to the night side would be far more efficient than in our current world, potentially moderating the temperature extremes that would otherwise develop. However, this heat transport would come at the cost of creating the most extreme weather patterns ever seen on Earth. Life in the twilight zones along the terminator line, where DEI meets night in eternal balance, unique ecosystems would emerge that represent life's last stand on a transformed Earth. These twilight zones would become narrow bands of relative habitability circling the planet, where temperatures remain moderate enough for liquid water to exist, and where some form of biological activity might persist. The landscape of these twilight zones would be unlike anything in Earth's current biosphere. Picture rolling hills and valleys where the sun hangs perpetually at the horizon, casting long shadows that never move but that vary in length as the elliptical orbit of Earth causes slight variations in the sun's apparent position. The light would have a unique quality, always golden and warm like an eternal sunset or sunrise, creating a landscape bathed in perpetual amber light. The temperature in these zones would be determined by the balance between solar heating and heat loss to space, moderated by the atmospheric circulation that brings warm air from the day side and cool air from the night side. The result would be a climate that might be compared to a mild spring day, cool enough to prevent the scorching heat of the day side, though warm enough to avoid the freezing conditions of the night side. Water would be the most precious resource in these twilight zones. Moisture would arrive primarily through the atmospheric circulation, as water evaporated from the day side would be transported by the global wind patterns and would condense out as it encounters the cooler conditions of the blast terminator zone. This precipitation might fall as gentle rain or even as snow at the cooler edge of the twilight zone, creating unique hydrological cycles. Rivers in the twilight zones would flow in patterns determined by the global atmospheric circulation rather than by the familiar gravity-driven patterns we know today. Water might flow generally from the day side toward the night side, following the pressure gradients created by the temperature differences. But the specific patterns would be influenced by local topography and the complex wind systems generated by the global circulation. These rivers would be unlike any in our current world, fed by precipitation from the perpetual storms along the terminator line and by runoff from the melting ice that forms where the twilight zone meets the night side. They would carry enormous volumes of water across the boundary between the habitable zone and the frozen night side. Some of this water would freeze as it enters the colder regions, forming ice dams and glacial formations that could create unique landscape features. Lakes in the twilight zones might form where local topography or wind patterns create areas of water accumulation. These bodies of water would have unique characteristics, neither frozen like the night-side waters nor boiling like the day-side waters. They might be among the few places on the planet where aquatic life could survive, creating oases of biological activity in an otherwise largely lifeless world. The plant life that might evolve in these twilight zones would need to adapt to the unique light conditions of the eternal sunset. Photosynthesis would need to be optimized for the specific wavelengths and intensity of light available at the horizon, which would be different from the full-spectrum sunlight that plants currently use. The red-shifted light of the perpetual sunset might favor plants that can efficiently use longer wavelengths of light for photosynthesis. These plants would also need to adapt to the constant wind conditions created by the global atmospheric circulation. The steady flow of air from the night side to the day side would create a persistent wind that would affect every aspect of plant growth and reproduction. Plants might evolve to be extremely wind-resistant, with flexible stems and small leaves that can withstand the constant air movement. The lack of daily temperature cycles would require plants to develop new strategies for managing their energy and growth. Without the familiar pattern of warm days and cool nights, plants would need to find new ways to regulate their metabolic processes and coordinate their growth and reproduction. Some plants might develop internal rhythms based on other environmental cues, such as slight variations in light intensity or atmospheric pressure. Pollination in the twilight zones would face unique challenges. Many of the insects and other animals that currently pollinate plants depend on daily activity cycles that would be disrupted in a world without day-and-night rhythms. New pollination strategies might evolve, perhaps involving wind pollination or the evolution of new types of pollinators adapted to the constant light and wind conditions. The animal life that might survive in the twilight zones would need to be extraordinarily adaptable. These animals would need to find food sources in an environment where most plant life has been eliminated and where the food webs that currently support animal life have collapsed. Scavengers might have an advantage, feeding on the remains of organisms that died during the initial catastrophe. Small mammals might be among the most likely survivors, as their size would allow them to find shelter in underground burrows or rock crevices, where they could avoid the worst effects of the constant wind and temperature extremes. These animals would need to be able to survive on limited food sources and would likely need to be omnivorous, capable of eating whatever plant or animal matter they could find. Birds might face particular challenges in the twilight zones. The constant winds would make flying difficult, while the lack of familiar landmarks and the absence of daily and seasonal cues would disrupt their navigation abilities. However, some bird species might adapt to the new conditions, perhaps becoming more terrestrial or developing new flight patterns adapted to the perpetual wind conditions. The migration patterns that currently characterize many animal species would be completely disrupted. Instead of the seasonal migrations driven by changing day length and temperature, animals in the twilight zones might develop new movement patterns based on the availability of resources or the need to move between different microclimates within the habitable zone. Insects might be among the most successful survivors in the twilight zones. Their small size and short generation times would allow them to adapt quickly to the new conditions. Some insects might evolve to take advantage of the unique conditions, perhaps developing new feeding strategies or reproductive cycles that are adapted to the constant light and temperature conditions. The soil ecosystem in the twilight zones would need to reorganize around entirely new patterns of nutrient cycling. The microorganisms that break down organic matter and recycle nutrients would need to adapt to the new temperature and moisture conditions. The constant wind might bring organic matter from the day and night sides, creating unique patterns of nutrient deposition that could support new types of soil communities. Fungi might play an increasingly important role in these ecosystems. Many fungi are adapted to survive in harsh conditions and might be able to persist in the twilight zones when other organisms cannot. These fungi could become the foundation of new food webs, decomposing organic matter and supporting the few animal species that manage to survive. The aquatic ecosystems in the twilight zone lakes and rivers would face their own unique challenges. These water bodies would be among the few places on the planet where temperatures remain suitable for most aquatic life, but they would also be subject to the unique chemical and physical conditions created by the TOMRI, global atmospheric circulation. Fish that survive in these waters would need to adapt to water chemistry that might be quite different from current freshwater systems. The water might contain dissolved minerals and gases from the extreme conditions on the day and night sides, creating chemical environments that current freshwater fish are not adapted to handle. Microscopic life in the twilight zone waters might be among the most successful survivors of the rotational halt. Many microorganisms are adapted to extreme conditions and might be able to thrive in the unique chemical and physical environment of these waters. These microorganisms could form the base of new aquatic food webs that support larger organisms. The atmospheric conditions in the twilight zones would create unique challenges for all life forms. The constant winds would affect respiration and water balance in animals, while the unique pressure and humidity conditions would influence how both plants and animals manage their internal physiology. Air quality in the twilight zones might be affected by dust and debris carried by the global wind patterns from the day and night sides. Animals would need to adapt to breathing air that might contain particles and chemical compounds that are not present in our current atmosphere. Where the longer timescales, the twilight zones might become centers of evolutionary innovation, where new species evolve to take advantage of the unique conditions. These species might be unlike anything in Earth's current biosphere, adapted to conditions that have never existed before in the planet's history. The ecosystems that develop in the twilight zones would represent life's attempt to adapt to the most extreme environmental change in Earth's history. While these ecosystems would be simplified compared to the complex webs of life we know today, they would demonstrate the remarkable resilience and adaptability of life in the face of seemingly impossible challenges. The deep Earth's response beneath our feet, hidden from direct observation but crucial to our planet's functioning, the deep interior of Earth would undergo profound changes in response to the cessation of rotation. These changes, occurring in the mantle and core thousands of kilometers below the surface, would have far-reaching consequences that extend from the generation of Earth's magnetic field to the patterns of volcanic activity and earthquakes that shape the surface. The Earth's core, a sphere of iron and nickel larger than the planet Mars, currently exists in a state of complex motion driven by heat and rotation. The outer core, composed of liquid metal at temperatures exceeding 4,000 degrees Celsius, flows in intricate patterns that generate our planet's magnetic field through a process known as the geodynamo. This process depends critically on the Coriolis forces created by Earth's rotation, which organize the chaotic thermal convection into the structured flows necessary for magnetic field generation. When Earth's rotation stops, the Coriolis forces that have shaped core dynamics for billions of years would vanish instantly. The liquid iron in the outer core would continue to convect due to heat from the inner core and radioactive decay. But without the organizing influence of rotation, these convection patterns would become chaotic and inefficient at generating magnetic fields. Imagine vast rivers of molten metal, each carrying electric currents capable of powering entire civilizations, suddenly losing the invisible forces that have guided their flow for eons. The complex helical patterns that currently characterize core flow would simplify into more basic thermal convection, similar to the circulation in a pot of boiling water, but on a scale that encompasses a volume larger than Earth's moon. The magnetic field generated by these simplified convection patterns would be much weaker and less stable than our current field. Instead of the familiar dipolar field with north and south magnetic poles, Earth might develop the complex multipolar field with many weak magnetic poles scattered around the planet. This field would fluctuate unpredictably, with magnetic poles appearing and disappearing over periods of years or decades rather than the slow, predictable wandering of our current magnetic poles. The weakening magnetic field would have immediate consequences for the charged particle environment around Earth. The Van Allen radiation belts, regions of trapped charged particles that currently surround our planet, would gradually dissipate as the weakening magnetic field becomes unable to contain them. The particles would either escape into space or precipitate into the atmosphere, creating aurora displays across much larger areas of the planet. As the magnetic field continues to weaken over months and years, Earth would become increasingly vulnerable to the solar wind and cosmic radiation. High-energy particles that are currently deflected by our magnetic field would begin to interact directly with the upper atmosphere, gradually stripping away atmospheric gases through a process called atmospheric shear. Sputtering. The effects of magnetic field collapse would not be uniform across the planet. Areas where magnetic field lines intersect the surface would experience the most intense radiation, while regions where the field provides some protection would remain relatively shielded. This patchy protection would create a complex pattern of radiation exposure that would affect both technology and any surviving life forms. Satellite systems and electronic infrastructure would be among the first casualties of magnetic field weakening. High-energy particles would gradually damage sensitive electronic components, causing satellites to malfunction and eventually fail entirely. The global positioning system, communication satellites, and weather monitoring systems would become unreliable and eventually inoperable. The core dynamics that generate the magnetic field would also influence other deep Earth processes. The heat transport within the core affects the temperature at the core mantle boundary, which in turn influences convection patterns in the overlying mantle. Changes to core dynamics could therefore affect the patterns of mantle circulation that drive plate tectonics and volcanic activity. The mantle, a layer of hot rock that comprises most of Earth's volume, would also respond to the sudden cessation of rotation, though more slowly than the liquid core. The solid mantle flows like a very viscous fluid over geological timescales, carrying heat from the core to the surface through convection currents that move at rates of centimeters per year. These mantle convection patterns are influenced by rotation through the same Coriolis forces that affect the core, though the effects are much smaller due to the mantle's solid state and slow flow rates. The loss of rotational forces would gradually alter mantle convection patterns, potentially changing the locations where hot mantle material rises to create volcanic activity. The immediate effects on mantle dynamics would be small, but over thousands of years, the changed convection patterns could lead to new patterns of volcanic activity and plate motion. Hotspots, regions where mantle plumes bring heat from deep within Earth to the surface, might shift location or change intensity as the underlying convection patterns reorganize without rotational influences. Plate tectonics, the process by which Earth's surface is constantly renewed through the creation and destruction of oceanic crust, might also be affected by changes in mantle dynamics. The forces that drive plate motion come from mantle convection, and alterations to convection patterns could change the rates and directions of plate movement over geological timescales. The immediate surface effects of the rotational halt would also influence deep Earth processes through changes in surface loading. The massive redistribution of water from the rotational catastrophe would alter the pressure on Earth's crust, potentially triggering earthquakes and affecting the patterns of crustal deformation. The accumulation of ice on the night side would represent a massive transfer of weight from the oceans to the continents. This redistribution could cause some regions of the crust to sink under the weight of ice, while other regions rebound as water is removed. These vertical movements of the crust, known as isostatic adjustment, would continue for thousands of years as the solid Earth slowly responds to the changed surface loads. The changed stress patterns in the crust could reactivate dormant fault systems and create new zones of seismic activity. Earthquakes triggered by the surface changes might be different in character from typical tectonic earthquakes, potentially occurring in regions that are normally seismically quiet. Volcanic activity might also be affected by the surface changes. The altered stress patterns in the crust could affect the movement of magma from depth to the surface, potentially triggering eruptions in some regions, while suppressing volcanic activity in others. The massive temperature changes at the surface might also affect the thermal structure of the upper crust in ways that influence volcanic processes. The hydrological cycle that transports water through the crust would be completely disrupted by the surface changes. Groundwater systems that have developed over millions of years would be drained toward the new ocean configurations, while other regions might experience groundwater flooding as surface water infiltrates through newly exposed areas. The chemical composition of groundwater would change as water interacts with rocks and minerals under the new temperature and pressure conditions. This could affect the stability of underground caverns and the transport of dissolved minerals that influence both surface and subsurface water quality. Deep crustal fluids, which play important roles in earthquake generation and mineral formation, would also respond to the changed surface conditions. The altered pressure and temperature gradients could change the flow patterns of these fluids, potentially affecting the generation of earthquakes and the formation of ore deposits. The permafrost that would develop on the night side would create a new type of frozen layer in the crust that could affect groundwater flow and crustal stability. As water freezes in soil and rock pores, it expands, creating stresses that could fracture rock and alter the mechanical properties of the upper crust. The thermal structure of the crust would be profoundly altered by the extreme surface temperature changes. The constant heating on the day side would create temperature gradients that extend deep into the crust, while the perpetual cooling on the night side would allow surface cold to penetrate much deeper than it currently does. These thermal changes would affect the mechanical properties of crustal rocks, making some regions more prone to fracturing while making others more plastic and deformable. The different thermal expansion and contraction rates of different rock types could create new patterns of stress that might trigger earthquakes or landslides. The overall energy balance of the deep Earth would also be affected by the surface changes. The altered heat flow from the surface could influence the cooling rate of the core and mantle, potentially affecting the long-term evolution of Earth's interior structure and magnetic field generation. The transformation of Earth's deep interior would represent one of the most fundamental changes in the planet's 4.5 billion-year history. While these changes would occur slowly compared to the immediate surface catastrophe, they would represent a permanent alteration to the planetary processes that have operated throughout Earth's history, creating a world that is alien not just at the surface, but from its core to its atmosphere. The unmaking of time in our exploration of a motionless Earth, we must consider one of the most profound transformations that would occur. The fundamental alteration of how time itself is experienced and measured on our planet. For all of human history, time has been defined by the rotation of our world, creating the basic units of days, hours, and minutes that structure every aspect of our existence. Without rotation, the very concept of time would need to be reimagined. The 24-hour day, perhaps humanity's most fundamental measure of time, would become meaningless on a non-rotating Earth. This unit, which has governed human activity since the earliest civilizations, exists only because our planet completes one rotation relative to the Sun every 24 hours. Without this rotation, the Sun would hang motionless in the sky above one hemisphere, making the concept of a solar day impossible to define. Consider how deeply embedded the daily cycle is in human consciousness and culture. We wake in the morning, work during the day, and sleep at night, following rhythms that have been consistent for thousands of generations. Our languages are filled with time expressions that assume the existence of day and night: good morning, midnight, midnight, dawn, dusk, dusk, high noon, and countless others that would lose their meaning in a world without rotation. The measurement of smaller time intervals would also be affected. Hours and minutes, while originally based on mathematical divisions of the day, have become so fundamental to human activity that their loss would create chaos in any surviving human societies. Imagine trying to coordinate activities, schedule meetings, or maintain any form of social organization without the common temporal reference points that rotation provides. Clock time itself would need to be completely reconceptualized. Currently, all human timekeeping systems are ultimately synchronized to Earth's rotation, whether through the atomic clocks that define international time standards or the simple sundials that have marked hours for millennia. On a motionless Earth, these systems would become arbitrary, disconnected from any natural phenomenon that could provide a universal reference. The concept of time zones, which currently divide Earth into regions that experience noon simultaneously, would become obsolete. Instead of the familiar map of time zones that circle the globe from east to west, any surviving human societies might need to develop entirely new systems for coordinating time across the planet's surface, perhaps based on distance from the terminator line or other geographic features. Biological time would face even more fundamental disruptions. The circadian rhythms that govern virtually all life on Earth are synchronized to the 24-hour rotation cycle, creating internal clocks that anticipate daily changes in light, temperature, and other environmental factors. These biological clocks would gradually drift out of synchronization without external cues, creating a form of permanent jet lag that could never be resolved. The psychological effects of losing the daily rhythm would be profound for any human survivors. Sleep patterns, which are closely tied to circadian rhythms, would become chaotic. The human brain relies on the daily cycle of light and darkness to regulate the production of hormones like melatonin that control sleep and wakefulness. Without these cues, sleep disorders would become universal among any surviving populations. Mental health would be severely affected by the loss of temporal structure. Many psychological conditions are influenced by circadian rhythms, and the disruption of these rhythms is known to trigger or worsen depression, anxiety, and other mental health issues. The complete loss of day-night cycles would create unprecedented psychological stress that could affect the cognitive function and emotional stability of survivors. Social organization would need to develop new temporal frameworks. Human societies have always organized themselves around daily and seasonal cycles, with work patterns, social activities, and cultural celebrations timed to coincide with natural rhythms. Religious practices, which often mark time through daily prayers or seasonal observances, would need to find new temporal foundations. The measurement of longer time periods would also be affected. Weeks, months, and years as we know them are based on astronomical cycles that would be altered on a non-rotating Earth. The week, an artificial 7-day cycle that exists in most human cultures, assumes the existence of days that would no longer occur. Months, originally based on lunar cycles, would need to account for the moon's altered behavior in the sky of a motionless Earth. The year, defined by Earth's orbit around the Sun, would still exist, but would be experienced very differently. Instead of the familiar progression of seasons marked by changing day length and weather patterns, the year would be marked by the slow migration of thermal zones across the planet's surface as Earth's axial tilt causes different regions to face the Sun more directly during different parts of the orbit. Seasonal celebrations that mark the passage of time in most human cultures would lose their meaning or need to be completely reimagined. Holidays that celebrate the winter solstice, spring equinox, or harvest time are based on astronomical and agricultural cycles that would be fundamentally altered in a non-rotating world. Historical records and calendars would become problematic for any surviving human societies. All recorded history is organized around calendar systems that assume the existence of days, months, and years as we currently understand them. The continuity of human cultural memory would be broken by the inability to relate pre-catastrophe time to post-catastrophe time in any meaningful way. The aging process itself might be affected by the loss of circadian rhythms. Many biological processes that contribute to aging are regulated by daily cycles, and the disruption of these cycles could accelerate or alter aging patterns in unpredictable ways. The measurement of human age in years would continue to be possible, but the biological meaning of age might change if aging processes are disrupted by the loss of daily rhythms. Communication across the transformed planet would face temporal challenges. Without universal time references, coordinating activities between different regions would become extremely difficult. Any surviving technological communication systems would need to develop new protocols for temporal coordination that don't rely on shared concepts of daily time. Navigation and exploration would also lose important temporal references. Many navigation techniques rely on the position of the Sun at specific times of day or the timing of celestial events. While some astronomical navigation would still be possible using the Moon and stars, the loss of solar time would eliminate many traditional wayfinding methods. The concept of productivity and work schedules would need complete reconceptualization. Human productivity patterns are closely tied to daily rhythms, with most people experiencing peak alertness and performance at specific times of day. Without these natural rhythms, any surviving societies would need to develop entirely new approaches to organizing work and rest. Scientific observation and measurement would face unique challenges without standardized time references. Many scientific phenomena are measured and characterized by their temporal patterns, and the loss of universal time standards would complicate scientific research and data collection for any surviving scientific communities. Weather patterns, which currently follow daily cycles of heating and cooling, would no longer provide temporal cues. The familiar progression of temperature changes throughout the day helps humans and animals anticipate and prepare for environmental changes. Without these patterns, surviving organisms would lose important environmental cues that help regulate behavior and physiology. The speed of environmental change would also affect temporal perception. Currently, most environmental changes occur gradually over daily and seasonal cycles, allowing organisms to anticipate and adapt to changing conditions. In a non-rotating world, environmental changes might be more abrupt and chaotic, making temporal prediction much more difficult. Even the basic human perception of time might be altered by the changed environmental conditions. Psychological research has shown that time perception is influenced by environmental factors like light levels, temperature, and activity patterns. The extreme and constant conditions of a non-rotating world might alter how any surviving humans perceive the passage of time, making minutes feel like hours or hours feel like minutes. The concept of simultaneity would become more complex across the planet's surface. Currently, it's meaningful to say that events happen at the same time because we share common temporal references based on Earth's rotation. On a non-rotating planet, simultaneity would need to be defined relative to other reference points, making temporal coordination across distances much more challenging. Memory formation and retrieval, which are influenced by circadian rhythms, might be affected by the loss of daily cycles. The human brain consolidates memories during specific phases of the sleep-wake cycle, and the disruption of these cycles could affect how memories are formed and recalled, potentially impacting learning and cognitive tree function in survivors. The planning and anticipation of future events would become more difficult without predictable daily cycles. Human planning abilities rely heavily on the ability to project daily and seasonal patterns into the future. Without these patterns, long-term planning would become much more challenging for any surviving societies. Even artistic and creative expression would be affected by the loss of temporal structure. Much human art and literature uses temporal metaphors and references that assume the existence of daily and seasonal cycles. The entire vocabulary of temporal expression in human languages would need to evolve to match the new reality of a timeless world. The transformation of time itself would represent one of the most profound challenges facing any survivors of Earth's rotational halt, affecting not just practical matters of coordination and organization, but the very foundations of consciousness, culture, and human identity that have developed over millennia of life within the rhythm of a tingle, rotating world. The ocean's memory, the vast bodies of water that cover most of our planet, carry within them a memory of motion, a record of currents and temperatures that have circulated for millions of years in patterns driven by Earth's rotation. In the aftermath of rotational halt, these oceanic memories would be erased as the seas reorganize themselves according to entirely new principles, creating marine environments unlike any in Earth's history. Currently, our oceans are organized into massive circulation systems called gyres, enormous loops of current that redistribute heat around the planet and support marine ecosystems through the Baal. transport of nutrients and oxygen. These gyres exist because of the Coriolis effect created by Earth's rotation, which causes moving water to curve rather than flow in straight lines, creating the circular patterns that characterize ocean peak. Circulation. The Gulf Stream, perhaps the most famous of these currents, carries warm water from the Gulf of Mexico northward along the eastern coast of North America before turning eastward across the Atlantic to warm the shores of Crete, Europe. This current system exists only because Earth's rotation deflects the flow of water driven by temperature and pressure differences, creating a stable circulation pattern that has persisted for millions of years. In a non-rotating world, these familiar current systems would gradually disappear, replaced by much simpler flow patterns driven directly by temperature differences between the hot day side and cold night side of Chaos, the planet. The complex, three-dimensional circulation that currently characterizes our oceans would be replaced by a more straightforward flow from cold regions toward hot regions, fundamentally altering marine environments worldwide. Picture the Atlantic Ocean without the Gulf Stream, the Pacific without the Kuroshio Current, the Indian Ocean without its complex seasonal circulation patterns. The absence of these currents would not simply mean that water stops moving, but rather that water begins moving in entirely different patterns, carrying different temperatures, nutrients, and chemical compositions to regions that have never experienced such conditions. The equatorial currents that currently carry warm water westward across the Pacific and Atlantic would disappear, no longer driven by the trade winds that depend on rotational forces. Instead, water movement would be dominated by the temperature gradient between hemispheres, creating north-south flows rather than the east-west flows that currently dominate equatorial regions. Deep ocean circulation, which currently brings oxygen-rich water from polar regions to the deep sea and returns nutrient-rich water to the surface, would be completely reorganized. This circulation, known as the thermohaline circulation or the global conveyor belt, depends on the sinking of cold, dense water at the poles and its slow movement through the deep ocean to upwelling zones in other parts of the world. In a non-rotating world, this deep circulation would be replaced by a simpler pattern driven by the temperature contrast between the day and night sides. Cold water from the night side would sink and flow along the ocean floor toward the day side, where it would be heated and rise to the surface, creating a global circulation pattern that is much simpler but potentially more vigorous than current deep ocean circulation. The upwelling zones that currently bring nutrients from the deep ocean to the surface, supporting some of the most productive marine ecosystems on Earth, would shift to entirely new locations. These zones, which currently exist where winds and currents conspire to bring deep water to the surface, would be replaced by upwelling driven by the thermal circulation between day and night sides. Marine life would face unprecedented challenges as the ocean circulation systems that have supported life for millions of years disappear and are replaced by new patterns. Fish migrations that follow ocean currents would be disrupted as the currents they depend on vanish or change direction. Species that depend on nutrient upwelling in specific locations would find their food sources relocated to distant parts of the ocean. The temperature structure of the oceans would be completely altered. Currently, ocean temperatures are moderated by the constant circulation that mixes warm and cold water masses. In a non-rotating world, the oceans would develop much sharper temperature gradients, with extremely hot water on the day side and very cold water on the night side, separated by relatively narrow zones of tannery. Intermediate temperature. This temperature structure would create density gradients far steeper than any in our current oceans, driving circulation patterns that would be more vigorous but less stable than current ocean currents. The mixing of water masses with very different temperatures and chemical compositions could create unique marine environments with characteristics unlike any in our current oceans. Sea ice formation would follow entirely new patterns as the permanently cold night side develops ice coverage that could extend much farther toward the equator than any ice in our current world. The boundary between ice-covered and ice-free ocean would become a zone of intense oceanographic activity as warm water from the day side meets cold water from the night side. The chemical composition of seawater would be affected by the new circulation patterns and temperature distributions. The solubility of gases in seawater depends on temperature, so the extreme temperature variations would create regions with very different oxygen and carbon dioxide concentrations. Some areas might become oxygen-depleted dead zones, while others might be supersaturated with dissolved gases. Ocean acidification, currently caused by the absorption of carbon dioxide from the atmosphere, would follow new patterns as the changed atmospheric circulation alters the distribution of carbon dioxide above the oceans. Some regions might experience severe acidification, while others might see reduced acidity, creating a patchwork of chemical conditions that would challenge marine life in new ways. The formation of sea ice would create unique challenges for ocean circulation. As water freezes, it excludes salt, making the remaining liquid water more dense and causing it to sink. In a non-rotating world, this process would occur over much larger areas than in our current world, potentially creating massive convection currents as dense, salty water sinks and is replaced by less dense water from other regions. Coastal environments would be completely transformed by the changed ocean circulation and sea level patterns. Beaches, tidal pools, and coastal wetlands that have existed for millions of years would be replaced by entirely new coastal environments adapted to the new patterns of wave action, temperature, and sea level. The waves themselves would be generated by different mechanisms in a non-rotating world. Currently, most ocean waves are generated by winds that blow across the ocean surface, and these winds are influenced by rotational forces. In a non-rotating world, wave generation would be dominated by the strong, steady winds flowing from the night side to the day side, creating wave patterns that might be more uniform, but potentially more powerful than current ocean waves. Tsunamis and other extreme wave events would also follow new patterns as the changed ocean circulation and coastal geometry create new pathways for wave propagation. The massive initial redistribution of ocean water following the rotational halt would create wave patterns that might persist for years or decades as the oceans gradually settle into their new configuration. The seasonal patterns that currently affect ocean temperatures and circulation would be replaced by different cyclical patterns as Earth's orbit around the Sun causes the thermal zones to migrate slowly across the planet's surface. These new seasonal patterns would be much slower and more gradual than current seasons, creating long-term cycles in ocean temperature and circulation that would be unlike any cyclical patterns in our current oceans. Marine ecosystems would need to adapt not only to the changed physical conditions, but also to the altered timing of seasonal cycles. Many marine organisms timed their reproduction and migration to coincide with seasonal changes in temperature and food availability. The much slower seasonal cycles of a non-rotating world would require completely different adaptive strategies. The interaction between the oceans and the atmosphere would also be transformed. Currently, the oceans and atmosphere exchange heat, moisture, and gases through processes that depend on the relative motion between air and water masses. In a non-rotating world, these exchange processes would be dominated by the strong temperature gradients rather than the complex wind and current patterns that currently drive ocean-atmosphere interactions. The memory of motion that currently characterizes our oceans, with water masses that can be traced to their origins thousands of miles and years away, would be replaced by a simpler but more extreme circulation that would create entirely new patterns of oceanic memory, carrying the signature of the day-night temperature contrast to every corner of the marine world. The conclusion. The eternal dance as our journey through this transformed world draws to a close, we return to where we began, with a new appreciation for the profound elegance of Earth's rotation and the countless ways it shapes every moment of cash. Our existence. What began as a simple question about planetary motion has revealed itself to be an exploration of the very foundations of life, time, climate, and consciousness itself. The scenarios we have traversed together paint a picture of a world so fundamentally altered that it challenges our deepest assumptions about the nature of our planet and our place upon it. From the catastrophic redistribution of oceans and atmosphere in the first moments after rotational halt, to the slow reorganization of life itself in the narrow twilight zones, every aspect of Earth would be dabbler, transformed beyond recognition. Yet in imagining this alien world, we have gained insight into the remarkable precision and delicate balance that characterizes our actual planet. The 24-hour day, the familiar seasons, the gentle trade winds, the ocean currents that moderate our climate, the magnetic field that protects us from cosmic radiation, all exist because our planet maintains its ancient dance through space with exactly the right speed and orientation to sustain the complex symphony of life. The thought experiment reveals how many systems we take for granted actually depend on rotation. The very air we breathe circulates in patterns shaped by Coriolis forces. The water we drink has been transported around the globe by currents that exist only because Earth spins. The soil that grows our food has been enriched by weather patterns that depend on the daily cycle of heating and cooling. Even our sleep patterns and the fundamental rhythm of our consciousness are synchronized to the rotation of our world. Consider the extraordinary chain of cosmic coincidences that has created the conditions we enjoy today. Earth formed at just the right distance from the Sun to maintain liquid water. Our planet acquired just the right amount of rotational momentum during its formation to create days that are neither too long nor too short for complex life to flourish. The Moon formed at just the right distance to stabilize our rotation without disrupting it entirely. Our magnetic field achieved just the right strength to protect us from radiation while allowing beneficial cosmic processes to continue. This series of cosmic accidents has created a world where the most complex and beautiful phenomena can emerge and persist. The migrations of animals across continents, the seasonal flowering of plants, the formation of weather systems that bring life-giving rain to distant regions, the development of human civilization with its arts and sciences and technologies all depend on the continuation of processes that operate on scales far beyond human control. The ancient storytellers who imagined the sun standing still understood something profound about our dependence on cosmic order, even without the scientific knowledge to explain the mechanisms involved. Their stories captured the essential truth that the stability we experience is not guaranteed, but depends on the continuation of forces that have operated unchanged for billions of years. Modern science has given us the tools to understand these forces in unprecedented detail, but it has also revealed how remarkable our situation truly is. Among the thousands of exoplanets now known, Earth appears to be unique in its combination of characteristics that support complex life. Our rotation rate, our atmospheric composition, our distance from the Sun, our magnetic field strength, and countless other factors all fall within narrow ranges that permit the existence of the intricate web of Tren, relationships that make life possible. This understanding brings with it both wonder and responsibility. We are the inheritors of a world shaped by 4.5 billion years of cosmic evolution, a world where countless random events and gradual changes have combined to create conditions of extraordinary complexity, and beauty. The systems that maintain this world operate on scales far beyond human influence, yet we have developed the power to affect many of the delicate balances that these systems maintain. The vision of a motionless Earth serves as a powerful reminder of what we have to lose. Every ecosystem, every species, every beautiful landscape exists within the narrow envelope of conditions that Earth's rotation helps to maintain. The thunderstorms that water our crops, the ocean currents that moderate our climate, the magnetic field that protects us from harmful radiation, all depend on the continued spinning of our planet through space. But this vision also reminds us of the resilience and adaptability that characterize natural systems. Even in our most extreme scenario, life would find ways to persist, adapting to conditions unlike any in Earth's previous history. The story of life on our planet is fundamentally a story of adaptation and survival in the face of changing conditions. From the first microorganisms that learned to harness solar energy to the complex ecosystems that have weathered ice ages and mass extinctions. Yet resilience has its limits, and the conditions that would follow the cessation of Earth's rotation would push those limits far beyond anything life has previously faced. The gradual changes that evolution can adapt to over millions of years are very different from the catastrophic, instantaneous changes that would follow a rotational halt. This brings us to a deeper appreciation of the present moment and the world we currently inhabit. The sunrise that greets us each morning represents not just the arrival of daylight, but the continuation of a cosmic process that has remained constant throughout human history and long before humans existed. The sunset that closes each day marks not just the end of daylight, but our planet's faithful completion of another rotation in its eternal dance around the sun. The changing seasons that mark the passage of time reflect not just the tilt of our planet's axis, but the complex interplay between rotation, orbital motion, and atmospheric circulation that creates the familiar patterns of temperature and weather that have shaped human culture for millennia. The predictable cycle of warm summers and cool winters, wet seasons and dry seasons, has allowed human societies to develop agriculture, plan for the future, and create the complex civilizations that past that characterize our modern world. Even the evolution of human consciousness has been shaped by the rhythms that rotation creates. Our concepts of time, our sleep patterns, our seasonal celebrations, our understanding of cause and effect, all developed within the framework of a rotating world. Our languages are filled with temporal and spatial metaphors that assume the existence of daily and seasonal cycles. Our religions and philosophies have been shaped by contemplation of the cosmic order that governs our existence. In losing rotation, we would lose not just the physical conditions that support life, but many of the conceptual and cultural frameworks that make human existence meaningful. The very notion of progress, which assumes that time moves forward in a predictable manner, depends on the stable temporal framework that rotation provides. The thought experiment ultimately leads us to a profound sense of gratitude for the cosmic inheritance that makes our existence possible. We live within a system of such intricate beauty and precision that even our most sophisticated scientific instruments can only begin to capture its full complexity. From the quantum mechanical processes that govern molecular interactions to the gravitational forces that hold galaxies together, we exist within a universe that seems almost impossibly fine-tuned for the emergence of complexity, consciousness, and beauty. Yet this fine-tuning is not the result of design, but of the deep principles of physics and chemistry working themselves out over cosmic timescales. The beauty and complexity we see around us emerge naturally from the fundamental laws of nature, given enough time and the right conditions. Earth's rotation is not a gift but a consequence of the physical processes that formed our solar system. Yet the consequences of that rotation are so beneficial for life that it might seem like a gift. This perspective transforms our relationship with the natural world from one of casual indifference to one of profound appreciation and careful stewardship. Every breath of air, every drop of water, every ray of sunlight represents the culmination of billions of years of cosmic evolution. The stable climate that allows our civilizations to flourish, the diverse ecosystems that support countless species, the predictable seasons that allow us to plan and build for the future, all depend on the continuation of processes that we cannot control, but that we can certainly affect through our actions. The exploration of a motionless Earth reveals the extraordinary nature of our rotating Earth and reminds us that we live within what might be called a cosmic Goldilocks zone, where not just one or two factors, but countless factors must be just right for life to flourish. This realization brings with it both humility about our place in the universe and responsibility for protecting the conditions that have made our existence possible. As we close this journey through transformed worlds and cosmic possibilities, we are left with a renewed sense of wonder at the ordinary miracle of rotation that continues even as we contemplate its absence. Every moment our planet completes a little more of its daily revolution, carrying all of life along on its ancient journey through space. In that simple motion lies the foundation of everything we know and love, the rhythm that makes possible not just our existence but our consciousness of existence, our capacity to wonder about our place in the cosmos and to imagine worlds both real and impossible. The next time you watch the sun move across the sky, feel the wind on your face, or simply notice the passage of day into night, remember that you are witnessing the effects of forces that have shaped our world for billions of years and that continue to shape it still. In that rotation lies not just the physics of planetary motion, but the very foundation of time, life, consciousness, and beauty itself, spinning endlessly through the cosmos, carrying the eternal dance of existence forward into an infinite future of possibility and wonder.